welcome everybody. I'm so happy to be here today to celebrate Geli Fest, Maria's Fest. But before introducing it formally, I want somebody to speak before me. So please, Aharon. Aharon Davidson. Aharon Davidson is a prominent researcher in high energy physics, and he was also supervisor of Maria Bovmevian. So please, Aharon.
Hi, Maria, do you see me? Okay, let me just, all the best, and let me just move to the share screen. Just a moment, I'm with you. Okay, now I think, right. Okay. The title is familiar to you, some of you. It is a view from, not from the Dirac cone, but from the Davidson cone. This is a very special cone in which only me and Maria are there. So here we are. Well, who would have believed it? Dear Maria is already 70 years young. And here I am, Maria's PhD supervisor, being honored to join her retirement fest. What a pleasure indeed. Now that Maria has already earned a world recognition for her significant contributions to the understanding of graphene and many other condensed matter systems, it is perhaps a good time to pause and to be reminded how it all started. We met in the Weizmann Institute. If I recall correctly, it took place back at 1982 or 83. I vividly remember how Maria has landed in my room, just like this, out of the blue, introducing herself as a Spanish student interested in the main contemporary problems in theoretical physics. Must confess, I still do not have the finest idea what brought her to the Weizmann Institute in the first place. Hopefully one day I will get some pedagogical hint. My experience with supervising students was quite limited at the time. My first student was Kobe Sonnenschein, who preceded Maria. But the chemistry between Maria and myself has really puffed out on the spot. No wonder there was no way whatsoever to miss the observation that Maria was loaded with mathematical skills and originality. And let me put in parentheses, citing Maria, she always said that there are always with her unavoidable stupid mathematical mistakes along the way. I haven't seen any, but I fully agree with her. She is full of energy, imagination, and humor. Really a perfect student, a true colleague, and a pleasure to collaborate with. As you can imagine already, it was never just physics. Never just ideas, data, and calculation. No doubt, as far as our relations with Maria and Ángel are concerned, it went all the way down to the personal family level. A very special and lifetime friendship has been developed, which has remarkably lasted until this very day. In some respects, let me borrow momentarily a scientific language, one can even phrase that our world lines are classically entangled. Maria has visited us in Israel many times. Once as a Dozo Fellow to Ben-Gurion University, lately as an invited speaker to my retirement fest, followed by a private visit a year ago, and many times in between. Respectively, me and my wife Zahava have visited Madrid many times as well. We also met once in the States during my sabbatical in Syracuse University, trying to locate a decent physics problem of mutual interest. Well, let me remind you that this was at the pre-graphene era, when Maria was a postdoc in Princeton. Maria's PhD research dealt with two topics, which are still of current interest nowadays. Our first two published papers were about the so-called horizontal, that is flavored Peccei-Quinn symmetry, with the focus put on the intergenerational Yukawa structure of the fundamental fermions. To be more specific, we have studied the interplay of the vacuum manifold structure and the flavor interaction, demonstrating how to avoid the domain wall problem without invoking exotic fermions and or extra gauge interactions. The associate flavor axion, coined as familon by Wilczek, still makes a viable dark matter candidate today. And here is a picture of the two articles sent. One's domain wall, horizontal epilogue, and the other one, also the same topic, horizontal axion alternative, the interplay of vacuum structure and flavor interactions. Our other trail of research had to do with cosmology. It was a bit later. These were the days, to remind you, when the Kaluza-Klein theory has made its resurrection and cosmological compactification of the fifth dimension played a central theme. Our contribution to the subject was to show how the fine structure constancy is asymptotically respected only provided the effective four-dimensional cosmological constant vanishes and the ordinary tree space is open. And here again are the two other papers, four altogether, about cosmological compactification and the role of extra dimensions in cosmology. And here is a nice bonus. Some of you were probably exposed to my own picture as a young assistant professor in the Weizmann Institute, as is proudly presented in Maria's homepage. I'm still there, very difficult to recognize myself. However, all of you are probably not aware of the successive picture that I found establishing the final proof that Maria was once young and well. The arrow is just to assure the correct identification. Look at Maria, unbelievable. And finally, dear Maria, I don't want to take too much time with my short beginning presentation. You are now at your prime time. You recall that 70 is just not even a prime number, not necessarily a stop sign, not even a slow sign. Keep walking along your unique and so successful scientific trail, as there are plenty of physics problems awaiting your professional wisdom. Me and Zahava wish you, Ángel, and the family all the best. Dear Maria, you have made us so proud. You, Aharon. Bye-bye.
To celebrate Geli Fest and honor her capacity and responsibility as a mentor. Okay, so I think this photo will come up several times. It's in 1975, and it was a very important date in Spain because Francisco Franco died. I guess it was a time full of hopes and wonders and challenges, and I guess we will hear more about it. So here there are several people in this institute. Maria is here, and someone will tell us, so please don't tell now. Paco is also there. Mari Carmen is also there, and Pilar López Sancho is there. So if you haven't seen it, oh, it doesn't work. No? Okay. So there. Okay. And we have heard about her time in her thesis. So I don't have any more to add here with her thesis with Aharon Davidson. And then in 1986, she started her postdoc in the group of Wheaton in Princeton. A little bit before, I want to say that this is a personal view from Eduardo and me. There might be many things that we have missed that are also very important in her career, and I apologize for that. So this is the ones that we have chosen. That before this, fullerenes were discovered, a little bit before. And soon, I don't know what happened here. I think Paco will tell us how Maria went from high energy to condensed matter physics. Yeah, there is, that is not, no? Maybe here? Or? Okay. In 1992, this continuum approximation to Fullerene molecules was the first contribution to condensed matter physics from Maria, Jose, the group of the three, Jose, Paco, and Maria. And it was the first time that gauge fields were used to model deformations. And this has enormous impact now in condensed matter. Okay, still not going. Okay, and then this paper is called the Bible. You can imagine the importance of the paper. They predicted the renormalization, the Fermi velocity renormalization, and this was proved experimentally 17 years later. And I really love this book. She was very brave with the authors to write this book at the very beginning in 1995. And I love this book because this book was the main book for me in my thesis to study the Fermi liquid. And this was at the time when Maria was at Carlos III University, and I guess Luis Bonilla will tell us more about this time. And then this is me going to Carlos III and meeting Maria, and I was already met her at Autonomous University when I did my degree in physics. And when she was a teacher, and I had her as a teacher, it surprised to me two things. Once, she was very inspiring. She was inspiring all the time with many ideas. And the other, she cared about the students. And for me, this was wow. And then when I saw her at Carlos III University, I told myself I had to do my PhD with her. And well, here we are. And we started to do some walks there in Leganés. And we still do it today now at Autonomous University in this wonderful forest that is behind here. Well, these walks are about, oh, sorry. Oh, what's, espérate. Sí. Well, I'm very sorry, Eduardo. I'm a disaster. Well, these Socratic walks is a sentence that Maria loves, that where we come from and where are we going, okay? Okay. So now Dirac's PhD came. This is Alberto Cortijo. Fernando de Juan, and Fito. And we will listen more from Eduardo about this time, and we will listen more about these wonderful researchers later on. Eduardo.
Hi. So good morning, everyone. Thank you, Belén. So I'll take over from here. So this is the pointer. Very good. And let me, Adolfo, 2013, I believe, right, the PhD. And, but let me go back just a little bit, 2009, Ben-Aske, when Paco, Maria, and Mikhail Katsnelson organized this wonderful conference on graphene. You can see, so this is the group photo, Maria there, Paco in the middle. Misha is not in this photo, but he was there. There he is. And for me, it was a very nice conference for many things, but also because this was the first time that we presented our work, our first work, the work coming from this collaboration with Maria and Pilar. And so thank you very much. Thanks a lot, Maria, for allowing me to have fun doing physics with you. And so very nice. And this is 2009, 2010. This is, this meeting, incredible, right? 2 Nobel laureates were attending this, future Nobel laureates were attending this meeting. So Andrea Geim here giving his lecture. And the other one is not Katsnelson, is Aldain was also there in attending this Ben-Aske meeting. And so 2010, Maria was invited to the Nobel Symposium. Here she is, House. And 4 months later or so, Andrea Geim and Katsnelson were announced Nobel Prize winners. So Maria is definitely among, or one of the prominent women in graphene, here with Irina Grigorieva, Annalisa Fasolino, and Eva Andre, Pilar Lopez-Sancho. And 2010 was also the year of publication of this very nice, highly cited review on gauge fields in graphene with Paco and Mikhail Katsnelson. But you know, Dirac physics appears in graphene, but appears also in topological matter. I mean, topological matter is full of Dirac. So it quite naturally became an important research topic to Maria. And first in 2 dimensions, and I'm very glad that I participated in these so-called family papers, and later in 3 dimensions as well, here with Alberto, Iago, and Karl, and also with Maxim and Adolfo, but they are not in the picture. Talking about Iago, so 2016 PhD defense of Iago on emergent gauge fields and topological effects in Dirac matter. And 2016 is also the year of publication of another review, novel effects of strain in graphene and other dimensional systems. And this is an interesting review because, for many things again, but because these 13 authors, they all were at some point members of the theory group at ICMM. And I don't know if there is a picture with all of them. I found this one. And you can see here 9 out of 13. Rafa, Alberto, Maria, Mauricio, Vicente, Paco, Bruno, Hector, and Pablo. I guess Bruno has a photo with more authors, but let's see. And 2016 is also the year of the Nobel for topological phases of matter and topological phase transitions. Here is Aldain, 7 years after Ben-Aske, right? So Maria continued to work in topological matter. And this is a very nice work. I mean, a great example of cross-fertilization between high energy physics and condensed matter physics. Very nice with Maxim and Alberto. And 2019, Vicente defended his PhD thesis. 2021, Oscar also defended his PhD thesis. And here we are, 2023, and celebrating this wonderful career, studying quantum field theory aspects of Dirac materials. And so congratulations. And but indeed, this is a celebration and not a farewell. And because I'm sure you'll be, I mean, having fun doing physics still for many years to come. So congrats for the new position. That's it. Thank you.
So good morning, everyone. I'm José Ángel Silva from Imdea Nanociencia. We can start now the first session of the morning. Geli and I met in 2012 when I did a short stay at Paco's group. Although our approach to the tackling the condensed matter physics problems is very different, she was very welcoming and, more importantly, understanding. In fact, one of the things that I most admire about Geli is how she always organized the famous Blackboard group meetings and renormalization group classes so that the students had the best formation possible. The first speaker is going to be Paco Guinea. A view from the Dirac cone, Geli Fest.
I need it. Okay, it's great to be here. I'm very glad to be able to participate in this event. And I think I will be brief, so let me start. I will start with a picture of what was already shown. The only thing is that as I was there, I can give you a lot of juicy details, which have not been explained in terribly detail. Definitely, Maria Geli is there. There is Pilar López Sancho, Mari Carmen Muñoz. There is also Luisa González Sotos, and it's me. And if you notice, there are 5 research professors of CSIC in the same picture, and I think that says something about our generation. And all of us look very happy. I wonder why, because the truth is that we learned very little during the 5 years we went at the university. The university was, despite the effort of some people in the faculty, very, very mediocre, to say the least. And one of the reasons is in this other picture, which was taken right in the same spot from a different angle, and probably at the same time, more or less, a few months sooner or later. The university was all the time occupied by the police. Spain was ruled by a very cruel fascist dictatorship led by Francisco Franco. And probably we were also happy because we knew, as Bob Dylan said, that times were changing and times did change. And we also were happy because we were going to leave that university soon. Let me mention in addition that among other among other historic events, this picture was taken, I think, a few days after the end of the Vietnam War, which was definitely a big historic event. Okay, so then we parted ways. Maria went to the Weizmann Institute, as has been already explained. I went to the ITP Santa Barbara, 2 excellent, outstanding institutions, very different from the one we left where we made our undergraduate studies. Let me mention, because some of you have been at the ITP in Santa Barbara and at the present location of what is now called the KITP at the University of California in Santa Barbara, and it's a beautiful building overlooking the Pacific Ocean. But at the time I went there, it was just the 6th floor of the Ellison Hall, which is that building there. And the KITP, the ITP was started by, let me just mention this, by the American National Science Foundation, because there were not that many open positions available in theoretical physics at the time. And they decided to fund the ITP and to grant very good postdoctoral positions. So talented people didn't need to leave academia and could stay at places like the ITP until positions became available. A similar situation was happening at the same time in Western Germany, and they started a different program equally successful, the Heisenberg Fellowships. So I think this is a good example of the way things should be done in science. Now, we also, our ways were also separated because of the topics we choose. As it was said already, Maria went into high energy physics. and I went into condensed matter physics. Both of them were theories, but it seemed we were moving apart. That was not clear, that was actually not the case. And I'm trying to explain, I will explain it here. I would like to go through the activities which were being carried out in theoretical physics at that time, the late 20th century. There were a number of very interesting topics being discussed: the soft modes, the Goldstone modes, the Higgs modes, the renormalization group, the idea of broken symmetry, and at the end of the period, topology entered in a big way physics by means of the Berry phase and the quantum Hall effect. And all of them were common to high energy, to condensed matter, and to statistical physics. They had a common theme, namely, one was dealing with problems with an infinite number of degrees of freedom, either because high energy guys went to very high energies, or condensed matter guys went to very large sizes. And all of them had difficulties if you try to reduce them to a system to systems of non-interacting particles, because you hit upon divergences when you did the obvious thing, which was perturbation theory. And people in high energy, the main difference was that people in high energy worked in 4 dimensions in systems with a lot of symmetries, like relativistic invariance. And moreover, they really liked theories where you had logarithmic divergences. In condensed matter, we worked from 1 to 3 dimensions. The divergence could be anything. And in high energy, they were interested in what happened at very high energies, in what is called the ultraviolet limit. And in condensed matter, and in statistical physics, we were more interested in what is now called the infrared limit. The good thing about if you had a theory with logarithms, I will come back to it, is that a logarithm diverges both ways. So you can use the same techniques. Moreover, but the question is that these problems were tackled both in statistical physics, in condensed matter theory, and in high energy theory. And all you needed is to learn how to translate the terms from one topic to the other. And for that, in my case, it was very lucky for me to go to the ITP, because they foster the kind of collaborations between people with a high energy background and people with a condensed matter background. And I support the Weizmann Institute, another excellent institution, was doing the same. Okay, and then I will move to to our regroupment when we started to collaborate again. And as I was already said, that was with this very nice paper on the fullerenes. The fullerenes where this had been discovered slightly before this paper came out. I think it was Geli who approached me. We were both interested in field theories. We both knew that the honeycomb lattice, which was used at that time to describe graphite, nobody knew that monolayer graphene could be isolated, could be reduced to a kind of effective Dirac equation, because the dispersion of the fermions was relativistic. I think at that time, people in high energy, they had to make a difficult choice, because high energy was moving towards string theory, and a fraction of the high energy community moved into quantum information, and another fraction, like Geli, who wanted to stay doing more standard field theory, moved to statistical mechanics and condensed matter physics. And then I had some background from the ITP about how to talk to people with high energy knowledge. And we decided to check what happened, whether one could use the Dirac equation to describe the fullerenes, because we already knew that that there were fullerenes of many sizes. The Dirac equation describes systems with very many particles, which goes well beyond what you can do with atomistic models. So we thought, well, maybe these field theories help us to describe very large fullerene molecules. And what we found, I mean, the equation, at the end of the story is this equation, which is not that difficult. But what we found is a number of very interesting features. We combine the Dirac equation. Is the Dirac equation live in curved space? And the Dirac equation, by definition, has some kind of spin associated to the degree of freedom a particle in a honeycomb lattice has, because there are two sublattices. So you have to add a spin connection, which is something you need to borrow from general relativity. But not only that, the Fullerins, as already discussed by Euler in the 18th century, you cannot have a Fullerin only with hexagons, which is a honeycomb lattice. You need to have pentagons as well. The number of pentagons is fixed. All these objects have 12 pentagons. So you have to go slightly out of the honeycomb lattice of a which means of a simple Dirac equation. And we realize that the pentagons play the role of a magnetic vortex. I mean, you cannot break time reversal symmetry in a Fullerin, but actually you have, because of the spinor thing, you have two species of fermions, and then you have a magnetic vortex of one sign for one fermion and one magnetic field with the opposite sign for the other spinor. So altogether, in order to describe the Fullerin, you have to put a magnetic monopole, which is something which has yet to be observed at the center of the Fullerin. So we were combining everything you wanted and more, which has in field theory. And if you look at it in retrospect, nowadays that quantum materials and quantum objects are really fashionable, if we had found all these things now, we would have been much more famous than in that time, because at that time, nobody noticed that we were combining everything you can have in quantum mechanics and more. I think the subject is by no means close, and it's probably worth looking at it again. The problem with pentagons is that, now that we know about graphene, problem with pentagons is that graphene is very stable, very robust, and nobody until recently has ever seen pentagons in graphene, because they're very energetically, they're very costly until now. So here, for instance, you have a few recent papers where they discuss pentagons near edges in graphene river. So the study of pentagons and the fact that they're a source of a fictitious magnetic field, it's not the same field as coming from straight. So there are different types of fields which emerge in graphene. But pentagons and topology, I mean, a pentagon in the language of Landau-Lifshitz book on mechanics, on elasticity, is a disclination. And then you can also have pentagon-heptagon pairs, which are dislocations. In principle, you could expect in systems with three-dimensional features, that's what Euler's theorem says, you could find pentagons, and definitely you have pentagons or heptagons for the same matter. You will have these non-trivial and non-abelian, actually, gauge fields. Moreover, we are theorists, so we can go beyond C60, which is this stuff here, which is based on icosahedron, where you cut the vortices and the vortices become the pentagons. You can make a similar picture. Okay, you can put your honeycomb lattice on the faces of a tetrahedron, and you have something like C60, but it's not C60, and instead of pentagons, you have triangles. So you have also deviations from the honeycomb lattice. And this thing obviously is not going to happen in a graphene system, but now physicists, experimental physicists are quite capable of generating non-trivial setups artificially. So who knows if these situations where you have a combination of the Dirac equation and squares or triangles or whatever are possible. Let me also mention, this is one of the really big discoveries to be made this year, I think. This is a new type of microscope based on the STM developed at the Weizmann Institute by Shahalilani's group. And the idea is that you can tunnel and conserve momentum at the same time. And, and the point is that you have two-dimensional materials touching each other. One of them is on top of a pyramid, as shown schematically here. And you tunnel over a region of some maybe 100 nanometers. So it makes sense to talk about momentum at such scales. But the funny thing is that there is here a graphene layer sitting below a pyramid. So it's not flat. And if it's not flat, you need to have either wrinkles or disclinations or dislocations. So presumably this kind of setup will also be capable of studying topological defects in the lattice structure of graphene, because it's being forced upon it because of the induced curvature. And as I said, I think this system, this setup, this experimental situation has really a great feature in condensed matter physics. Okay, now we moved on. We knew about graphene, we knew about the Dirac equation, and then we realized that the Coulomb interactions in graphene define a renormalizable theory. I mean, it's if you put 1/r interactions in graphene and you try to do perturbation theory, you run into this problem of logarithmic divergences. If you have your Fermi energy at the edge of the Dirac cone, because graphene is neither a metal where Coulomb interactions are relatively easy to treat, or an insulator where Coulomb interactions are easier to treat, but it's in between. And then many parameters in the theory acquire a dependence on scales. And by scale, I mean either the frequency you're measuring your system with a photon at a given frequency, the frequency at which you use for the measurement will change the result. The temperature can do the same. The size of the system can do the same, even if you have strain. And the most relevant parameter where it already happens is the velocity, which defines the Dirac cones themselves. And we wrote that equation, and indeed, and I was at the time, I was later on, I was collaborating with an experimental group which was very, very skeptical about interaction effects in graphene until they measured it. And they reported it here. Maria made a comment on this paper. And this is the renormalization they observe of the Fermi velocity as function of the number of carriers, which is a way of putting an infrared cutoff in energy. And if you look at it, where is it? How can I go back? Oh. Okay, no problem. If you look at it, it's a renormalization by a factor of 3 almost. That, what has happened? No. No, that's it. Okay, so no, it will be 4 that. So. Okay, sorry. Okay. So what I mean is that, so this renormalization is much higher than the kind of renormalization you see in relativistic field theories which describe high energy particles. And moreover, in the same way that the Fermi velocity is renormalized, which is the most striking parameter which describes graphene, other quantities like spin orbit coupling and many other things are also renormalized, although not necessarily by the same amount. And by the way, here there is this issue, this kind of discrepancy between guys with a high energy background like Geli, or guys with condensed matter background like me. This divergence takes place at low energy. But for Geli, always the important thing was what happened at high energy. Luckily, a low divergence both ways. Okay, then we moved on. We analyzed gauge fields due to strains. It's a different gauge field. This is an abelian gauge field. The gauge field associated to pentanus that also mixes the flavors. The two flavors you have in the honeycomb lattice is non-abelian. But again, not only gauge fields due to strains, but they are relatively easy to observe experimentally. So let me summarize everything by saying that graphene is really a very friendly material towards theory. You can predict really interesting effects. You can predict really interesting effects, and they show up experimentally. And that doesn't happen so often in physics. I mean, this kind of agreement between theory and experiments. And that means that theory work, in the case of graphene, definitely, it's very useful in the advance of science, of research. Then let me just finish. We parted again. Geli is now working on wild semi-metals, which have three-dimensional Dirac cones. The topology of the wild metals is very interesting. I'm working in twisted bilayer graphene, which is like a metacrystal, a moire system in 2 dimensions, which, as probably many of you already know, has very, very interesting phase diagrams. And who knows what will happen in the future. But let me give you here, for instance, an example. You can have a 3-dimensional twisted system, and that probably combines the complication of these two systems. And experimentalists are coming closer and closer to the realization of systems like this. So it's going to be relevant in the near future. Let me mention as well a very nice article which appeared like a few days ago in the New York Times, which implies that there's plenty of time to do many things, basically. And that's it. By the way, I didn't notice that here is the normalization of the first development. Thank you very much.
So is there any question for Paco? If not, maybe we can move to the next speaker, who is Mikhail Katsnelson, online.
Yeah. Sorry, can you hear me?
Yes. Wait a second, I need to do some...
Then let me try to go to full screen. You can see the slide, right?
Yeah, perfectly.
Now it is the second slide, right?
Yes.
Okay, very good. Okay, first of all, it's really a great pleasure for me to participate in this exciting event. It's a pity for me that I was not able to come to Madrid in person, but it's good that we have now an opportunity to congratulate and to prize Maria also online. So I would like to tell about some recent works which we did on theory of graphene and other two-dimensional materials. I should especially thank Achille Mauri, my former PhD student. Actually, with him, most of the work was done. And also I have to thank Jan Loss and Annalisa Fasalin, with whom I worked in Nijmegen on this membrane aspects of graphene physics for many years. And first of all, I have to really to take an opportunity to thank Maria for a very pleasant and fruitful collaboration. So I know Maria almost from the very beginning of graphene boom, and this picture is made on Nobel Symposium in Stockholm, I think, in 2010. We published just 3 papers together, especially I think this review with Paco and Maria on gauge fields in graphene, which was mentioned already several times. Also, I really appreciate this first paper with Paco and Maria. I think it was one of the very first paper when the effects of these gauge fields, observable effect of gauge fields in graphene started to discussed. But apart from just 3 papers, we had a lot of other collaboration. In particular, indeed, as was already mentioned, we 3 of us organized this beautiful school in Benaske, which seems to be a kind of important event for graphene community in that time. Then we had exchange of students, PhD students with Maria, a lot of discussions on different subjects, especially I have to say that it was Maria who first convinced me that ADS-CMT is not just a nonsense, and actually it had some kind of important consequences for my future research plans. And now I would like to tell you something. Unfortunately, it is not about Dirac, but at least it is about quantum field theory and its application to the physics of 2D materials. So I hope it probably can also fit the scope of this event. I do not think that in this audience I need to tell a lot about 2-dimensional materials. We all know that there are plenty of them, and they have different electronic properties and also structural properties. Graphene is in a sense is the simplest because it is just flat at 0 temperature. Its analogs like silicon in Germany, and they already buckled. Also, we have more complicated materials like phosphorene, which is also buckled, but strongly buckled and strongly anisotropic. And I will not be talking about electronic properties of these materials, but about the structural and mechanical properties. And structural properties of graphene are very special. In particular, its extraordinary mechanical strengths. I think the main reason, 2 main reasons. First, it is the strongest chemical bond in nature. And second, and probably even more important, it's extremely difficult to create dislocation in graphene. That is why under very high deformation, it becomes mostly defect-free. And this is a picture of this cat in the hammock from the poster of Nobel Committee of 2010. They claim that 1 meter's hammock could sustain a cat. After that, with Jan Loss and Annalisa, we did a kind of quantitative calculations. But as a theorist, of course, we simplify a cat. And in 2 limits, when you have a point cat in the middle of hammock, it is about 3 kilograms. And if cat is homogeneously distributed over the whole 1 square meter hammock, then it is 8 kilograms. So indeed, it seems that it is more or less a reasonable estimate. Okay. Then, if we are talking about 2-dimensional materials, I need maybe to remind some really textbook material, textbook statements that 2-dimensional materials, actually they cannot be crystalline. 2-dimensional crystals do not exist, which was semi-qualitatively suggested by Peirce and Landau in 1930s. Then it was a kind of theorem known as Mermin or Mermin-Wagner theorem. And the point is that for conventional crystals, it's very important that mean square amplitudes of atomic displacements should be small in comparison with other atomic distances. But it is not the case in 2-dimensional crystals. Actually, you can analyze in general its phonon spectrum, and then you can see that apart from conventional acoustic modes, which corresponds to in-plane atomic displacements with linear spectrum, due to a very special symmetry, which was first noticed and emphasized by Ilya Lifshitz in 1950s, it is a symmetry with respect to rotation of 2-dimensional crystal as a whole in embedding 3-dimensional space, important theory which I will mention many times in my future talk. You have this flexural acoustic mode, which even more soft phonon spectrum, Q square instead of Q. And this is a kind of calculations, more or less realistic calculations of phonon spectra in graphene. And you can really clearly see that you have this flexural acoustic mode with quadratic dispersion and two in-plane acoustic modes with linear dispersion. As a result, if you calculate atomic displacement, then you immediately see that you have relatively weak logarithmic divergence at finite temperature for in-plane displacements, but much stronger displacements in that direction, in perpendicular direction. And naively speaking, you can say that crystal will not exist because of large atomic displacement. It cannot be also flat due to huge out-of-plane thermal fluctuations. But strictly speaking, the only thing what can be said that we cannot use harmonic approximation. And God knows what happens if we take into account properly anharmonic effects. But anyway, we can assume that flexural fluctuations are very strong. And as a result, probably you could expect that you would have not just a flat surface which you have at zero temperature in graphene, but you have some kind of ripples, corrugations, and probably the amplitude of these corrugations grow with the sample size, maybe not linearly like in harmonic approximation, but still something which should be taken into account. Since the dangerous modes are acoustic modes, then in principle we can forget about full lattice dynamics description, and we can come to continuous limit, which is just elastic theory. And elasticity theory for thin membranes or plates is described by the following expression for the effective deformation energy, which contains this bending rigidity, Laplacian h squared term, and kappa is bending rigidity coefficient at this. And then you need also to take into account a change of interatomic distances. You need to change deformation in plane. And it was known long ago, for more than 100 years, that in principle, in strain tensor, you need to take into account nonlinearities in out-of-plane deformations, because these deformations are very large. And if you do this approximation, and if you then just find the minimum of this energy, then you found these famous Foppel-von Karman equations, which are actually not about graphene, not about physics, but which are actually about real engineering, about strengths of airplane wings and other things. So it is very, very important, and it is all known, as I said, for long time. And very important, these equations are extremely nonlinear, which means that you can expect quite interesting and complicated phenomena even without thermal fluctuations. But if you take into account thermal fluctuations, then life becomes even more complicated. Actually, this theory of fluctuating membrane was started by David Nelson, Peliti, some other physicists in early 1980s. This was nicely summarized in this book edited by David Nelson and others. And you just use this Foppel-von Karman equation for the energy as a Hamiltonian, and then you build statistical mechanics. And in principle, if you neglect nonlinear terms, if you try to do harmonic approximations, then you immediately have nonsense. First of all, you immediately see, as I already have shown from lattice dynamics, that you have a huge out-of-plane fluctuations. Membrane cannot stay in flat. And also, if you just calculate explicitly correlation function at large distance, flat membrane assumes that this correlation function should go to constant when distance tends to infinity. It is not the case. So it was more or less known, but when Nelson, Lubensky, and other people started to discuss the theory of membranes, they probably kept in mind something really complicated, like biological membranes. But then around 2007, we realized that graphene is a kind of this Drosophila, kind of ideal model object for the theory of membrane, because it's extremely simple. We know interatomic interactions, we can do all calculations, and I think it was really kind of breakthrough in this development of theory of membranes when we started to, and then other people started to apply it to graphene. Okay, then a bit of mathematics. So if you do this approximation, taking into account quadratic nonlinearity in out-of-place displacements, but do not take into account quadratic nonlinearity in plane deformations U, then in field U, you have Gaussian functional integral in partition function, and in plane deformations can be integrated out explicitly. And then you have a kind of effective Hamiltonian dependent only on the fluctuations of H out of plane deformation. It is a type of H in power 4 nonlinearity, but much more complicated than, for instance, in conventional Ginzburg-Landau theory, because you have strong momentum dependence, you have very non-trivial tensor deformation, and two-dimensional Young modulus in plane elastic constant, some combination of them, plays the role of coupling constant for this field theory. Then analysis of this field theory by conventional methods of statistical mechanics suggests that you have scaling. That is why you have effective bending rigidity and effective Lamé constant, that is an effective elastic moduli, which are Q dependent. And you can establish some relation between different exponents. So you have only one independent critical exponent eta, which determines the renormalization of bending rigidity, and deformation of renormalization of elastic moduli then follows from this. And then importantly, that despite bending rigidity goes to infinity due to this nonlinearity, elastic moduli goes to zero. So actually elastic phonons becomes even softer. That is why it does not change Mermin theorem. Two-dimensional crystals cannot exist, but okay, it's another story. Okay, then we did just atomistic simulations for graphene, and it is just this correlation function. So you see really very nice crossover at some critical value of wave vector, which is roughly 0.2 inverse angstrom, and we can extract from these calculations critical exponents, which turns out to be 0.85. Actually, this is a picture of my graphene book, because what is here, it is not artistic view of graphene at finite temperature, it is just a snapshot from atomistic simulations. So it really how graphene should look like if you look with large enough magnification, and you really clearly see these ripples. And you see that at Q larger than Q star, your life is easy. So you have just harmonic behavior for the correlation function. And also, if you just calculate cross correlation function, which shows coupling between in-plane and out-of-plane deformation, you really see that above this Q star it is just zero, so you really can consider in-plane and out-of-plane deformations as independent. But at small q, you have a huge coupling between in-plane and out-of-plane modes, strong deviation from harmonic behavior, and this value of the exponent eta. This is experimentally confirmed. I think the most beautiful work is just this nice paper by McEwen and co-workers about so-called graphene kirigami, when you really see that effective bending rigidity in graphene at finite temperature can be several orders of magnitude larger than its nominal value. And also for in-plane for in-plane phonons, I did not show experiment because it is not so clear, but at least you can do atomistic simulations, and you really see that this effective Young modulus is also renormalized, and you really see a behavior of in-plane correlation function also in agreement with this theory by Nelson and others. And then the last question which we have is how to calculate the value of eta analytically. As usual in statistical mechanics, especially when it is similar to critical behavior, it's important to consider dimensionality and number of components of the order parameter as a free parameter. That is why let's assume that membrane is in a d small dimensional embedding space, and its dimension is d capital. So for real membranes like graphene, d capital is 2 and d small is 3, but let's consider as a free parameter. Then let's rewrite our Hamiltonian for this multidimensional case, and let's do the same approximation. Let's write strain tensor in linear approximation in plane deformation, and quadratic approximation in out of plane deformation. But strictly speaking, of course, in our model now H can be multidimensional vector, not necessarily just a number. Then the first nice way how to calculate eta, it was suggested by Ledusal and Radzikhovsky 30 years ago, and it is so-called self-consistent screening approximation. So you can consider this quantum field theory, you can build diagrammatic techniques, and this self-consistent screening approximation assumes, roughly speaking, summation of these bubble diagrams that is neglecting of vertex corrections. Then you have a closed set of equations for effective bending rigidity and for effective elastic modulus. Then you can solve this. And then you actually, if you put just d capital equal to 2 and d equal to 3, then you have a value of eta 0.82, which is quite close to the value of eta found in our Monte Carlo simulations. And actually it's very strange, because if you just consider where you can expect then this neglecting vertex correction should work, you can say that it is the case where number of components of field H, that is co-dimensionality of membrane in embedding space, tends to infinity. And actually it's an interesting question why it works so nicely already when this parameter, which should be infinity, is just equal to 1. Okay, then we can try to go beyond, and we can try to build more or less conventional normalization group and use epsilon expansion. Of course, it looks crazy because for theory of membranes, like for critical behavior, critical dimensionality is 4. We are interested in dimensionality 2. So epsilon equal to 2. So it definitely does not look like good expansion parameters. But nevertheless, we tried to do it with Achille Mauri, and for some reasons, which I will show in a moment, it turns out to be quite a successful story. So first of all, we reformulate, instead of considering initial elasticity theory Hamiltonian for arbitrary dimensionality, we introduced a new model, so-called Gaussian curvature interaction model, which coincides with true membrane for dimensionality equal to 2, but with generic parameters, it is different from elasticity theory. But nevertheless, it's easier to study, and analogs that, for instance, if you are interested in Heisenberg model, classical Heisenberg model, you can consider classical Heisenberg model just either like O3 model, and then you can generalize it as ON model, or you can consider it as SUN model for n equal to 2, and then you have another parameter. And in a sense, this Gaussian curvature interaction model, I would say it is just another way to introduce a formal small parameter in the system. So in three-dimensional case, you have this Hamiltonian. It is called Gaussian curvature interaction model because indeed the interaction term is expressed in terms of local Gaussian curvature, but you see you have quite non-trivial kernel growing, effective interaction grows like R square logarithm R. Then you do some trick, so you can use so-called Haber-Stratonovich transformation introducing some auxiliary field lambda. Then you build diagrammatic technique. Then you consider renormalization group. Then you hope that you will have fixed point, and then you study behavior of all characteristics of the system near the fixed point. By this way, we found a general expression for parameter eta up to epsilon square. And amazingly, if you substitute the true parameters for epsilon equal to 2, you see this huge, very huge smallness of coefficient at epsilon square, roughly 1,000. And so amazingly, for reasons which we do not maybe understand completely, we're extremely lucky because the real expansion parameter is not epsilon, but something like epsilon divided by 30. It turns out we can say that in theory of membrane, we have a funny situation when epsilon equal to 2, it still can be considered as a small number. So 2 is much smaller than 1. Okay. If you have scaling invariance, then of course the first thing which we wanted to check, maybe you have a full conformal invariance. Because if you have full conformal invariance, I'm not talking about two-dimensional system where you have this Virasoro algebra and so on, and you can have just exact solutions. But even in three-dimensionalizing model, as was nicely shown by Slava Rычkov and others, if you have full conformal invariance, then you can use bootstrap equations, you can find critical exponents with enormous accuracy. So if it would be the case of membrane, probably we could try to use this bootstrap to find eta. But then probably I do not need to explain technicalities. So full conformal invariance assumes, apart from dilatations and translations and rotations, also so-called special conformal transformation, which is a bit complicated. And it was a kind of common belief that normally in a generic interacting field, quantum field theory, if you have scaling invariance, you have conformal invariance. Okay, it follows from some detailed analysis of conditions of scale invariance, conformal invariance, and so on. So I have to say that actually it's very rarely when you have one but not another. But nevertheless, it turns out to be the case. In nonlinear membrane theory. In principle, it was known already shown by Cardi that Gaussian elasticity theory in linear approximation has scale invariance but no conformal invariance. But for some reasons, it was not so easy to expect this for interacting field. But nevertheless, we have shown that it is also the case. You do not have full conformal invariance, and the reason that you have this special symmetry, and this symmetry which I already mentioned, it is symmetry with respect to rotation of membrane in embedding space. It protects virial current from having anomalous dimension, and then you have virial current with proper dimension which breaks conformal theory. So and then the very last part of my talk, I think I still have some time. It is about quantum membranes. This is extremely complicated problem, which in particular we worked together with Paco, with other people, and it's a very controversial issue. But now I believe that we come to a complete solution, and I think now we know quite accurately what do you expect from membranes in the limit of low temperature, and in particular for graphene. I will focus on the problem of thermal expansion for the reasons which I will explain now. Because if you consider just conventional crystals, and if you consider just lattice dynamics and conventional harmonic approximation, that heat capacity at constant volume is represented as a contribution of different phonon modes. And if you consider acoustic phonons and three-dimensional crystals, you have this famous T-cube low dBi low for heat capacity. And thermal expansion, which I will consider it as a derivative, omega is either volume for three-dimensional system or area for two-dimensional systems, and Maxwell relation. Importantly, that thermal expansion coefficient can be expressed also as a derivative of entropy with respect to a pressure at a given temperature. And if you take this into account in so-called quasi-harmonic approximation, when you still formally use harmonic approximation, but assume that phonon frequencies are dependent on external parameters like volume of the system, then you find this Grunasian low. So actually heat capacity turns out to be, thermal expansion coefficient turns out to be proportional to heat capacity, and the proportionality coefficient is just weighted so-called microscopic Grunasian parameters, and normally it goes to some constant. Therefore, thermal expansion coefficients vanish at zero temperature at heat capacity. But some time ago, we noticed in work with Paco that two-dimensional crystals are quite special. Because these flexural modes, which are the most important mode for two-dimensional crystals under construction, under expansion, when you apply pressure, they become much harder. Actually, this Grunasian parameter for this mode, it is negative, and it's formally divergent at the limit q tends to 0. This was a kind of just analytical expression, but if you look just as calculations from atomistic dynamics of these Grunasian parameters, then you really see that it becomes negative and very large. And then from naive theory, you can assume that you are, for thermal expansion, you are always in quantum classical regime, because Q of the order of Q star, where nonlinear effects turns out to be important, still corresponds to the regime where frequency of phonons are much smaller than temperature, and then it is still classics. And then we found this kind of estimate of thermal expansion coefficient of graphene as negative and almost temperature independent, which by the way is in kind of, despite very simple theory, in a kind of reasonable agreement with experiment. But it's bad, because as I will show you in a second, it contradicts that law of thermodynamics. It cannot be like that. And after several attempts, I believe we made a consistent quantum theory of membranes. I think the first work in collaborations with Igor Burmistrov and Sasha Mirlin and his group in Karlsruhe, we semi-guessed, I would say, the correct answer. But then in a recent paper with Achille Mauri, we built really quantum field theory, and now we are quite sure that this result is correct. So what is the difference between quantum membrane and classical membrane? Just if you use formalism of path integrals, that's the only difference, that in quantum case you have additional dimension. So imaginary time turns out to be additional dimension. And then you still have effective action. But you need to add to potential energy, which you always have, you need to add also kinetic energy. And then you need to analyze this partition function. It means that in green function, you need to take into account omega, you need to take into account frequency. And in harmonic approximation, you have the following quite simple expressions for the green functions for in-plane and out-of-plane phonons. But then it is crucially important that we need to make a dimensional analysis, and we need to throw away the terms which are not of the leading order, which are not the most divergent. And very importantly, that there are several such terms and they should be either taken into account simultaneously or neglected simultaneously. If you keep one of them but neglect another one, then it's very dangerous because you formally break the symmetry with respect to rotation of membrane into embedding phase, and you can have some kind of unphysical contributions. And this analysis shows that the minimal action is just like that. So you need to take into account kinetic energy only for out-of-plane deformations. Then you still can neglect quadratic terms in in-plane deformations in strain tensor. If you take into account here also U dot term, then you need to take U in power 4 terms. It's very important, otherwise you can break asymmetry. And also analysis show that now the critical dimension in quantum case is 4. But we are in dimension 4 because effective dimension for quantum phase transition, as we know from Hertz, from ND millis, it is just D plus Z, where Z is dynamical critical exponent. For flexural phonons, Z is equal to 2. So two-dimensional membranes exactly corresponds to critical dimensionality 4. And in critical dimensionality theory is renormalizable. We have proven renormalizability of this theory in a kind of rigorous way based on renormalization group analysis. You have only logarithmic divergence, not larger than Z. And then you found the following expressions for effective bending rigidity and effective Young modulus, which, as I said, were semi-derived, semi-guessed in our work with Burmistrov, Mirlin, and others. But now I believe we derive them in a quite accurate way. And the most important results are that effective Young modulus decreases, but in a very, very, very slow logarithmic way, where lambda is cutoff parameter, which tends to infinity. And bending rigidity increases, but also in quite weak logarithmic way. And also, if you take into account some external deformation, then you see that you can have some kind of deviations from Hooke's law. Effective bending rigidity turns out to be dependent on external deformation non-linearly. But if you just do real calculations, then you really see this extremely slow dependence, like logarithm deformation in power -1/7. In practice, of course, it is constant. But much more importantly, that if you calculate thermal expansion coefficient, this is a kind of rigorous answer, you see the thermal expansion coefficient vanishes at temperature tends to 0. As it should be from set law of thermodynamics, but it vanished in extremely slow way, just 1 divided by logarithm temperature in power 4/7 or whatever. And so the prediction is that actually the expression with for thermal expansion coefficient, which we derived in a very simple consideration with Paco long ago, more or less remains correct till very, very small temperature. You have just some very weak logarithmic corrections. And if you go to helium temperature and even below, then thermal expansion coefficient should remain more or less temperature independent and negative. I think it is a very strong prediction, which definitely worth to check experimentally. So to conclude, using of quantum field theory methods in theory of membranes, and as already Paco and other people mentioned, Maria was one of the pioneers of using quantum field theory methods in theory of graphene and other two-dimensional materials. It gives you quite satisfactory results. First, for classical regime, you are very lucky. You have this numerically small parameter in epsilon expansion, and then it means that you can use regular epsilon expansion to calculate the only unknown parameter in scaling theory of membranes, parameter eta of renormalization of bending rigidity. Unfortunately, we are not so lucky if we would have also full conformal symmetry then we would be able to calculate it even much more accurately, like Slava Rычkov calculated critical exponents for three-dimensional Ising model, but unfortunately we do not have it. But in quantum case, we have completely renormalizable theory, only logarithmic divergence, which can be rigorously summed up. And we came to a very interesting, I believe, conclusion that thermal expansion coefficient of freely suspended two-dimensional membranes should remain more or less constant till extremely low temperatures, till helium temperature and even below, something definitely worse to check experimentally. So that's all. So at the very end, I would like again to thank Maria for her huge contribution to physics, and in particular to physics of graphene and two-dimensional materials, for extremely pleasant for me and long-term personal communications and collaboration, and of course congratulate her with this kind of important date. Many thanks, that's all. Yeah. And thank you for your attention, of course.
Thank you, Misha. Is there any question?
Hello, Michelle. Yes, one question. In this nonlinear elastic field that you described, especially in the beginning, can you have solitons?
Probably yes. I don't know. We did not study it, but I think there were some other papers. I don't remember the author, Kifshar, I don't remember, who considered solitons and other nonlinear waves in two-dimensional crystals. I think yes, it should be there. You have nonlinearity. It should be something like that, I think.
Okay, thank you.
So if there is no further question, we can finish this session and go for coffee. Let's thank all the speakers again.
To the second session of this wonderful event. And our first speaker is Maxim from CNRS and the Institut Denis Poisson. So from Tours, and he will tell us how to make the universe chiral again.
So it's a first of all great pleasure to come here, Maria. Thank you very much for Karl also to inviting me to this place. It's a really wonderful event from you, really heart-touching, I would like to say. So since I have only 30 minutes, I would not say too much about what happens and how we got known together. Karl is catalyzer. At some point he said, okay, we have the campus. At our campus there is one building, actually this building, and there is one woman there who works on, maybe we will do some work. And finally that's how we got in touch together and started to write some papers. In fact, I wanted to write different. I wanted actually, if you look to the web page, the talk actually is different. Title is completely different. And just because at last moment I thought, wow, why we should talk about things which we did before, because I thought to discuss what we did, what could be the next things. Let me talk about something different, because in fact I'm impurity here. Yeah. Impurity means that I'm from high energy physics and actually not from graphene physics. And let me say something entertaining about things which are completely from different perspective. Yeah. So I'll try to use the device. First of all, actually, it's the first time in my life I'm giving the presentation PowerPoint, because I use Mac, because Karl told me a long time ago that Keynote is the best. So right now I use Mac, and that's all faults just to his direction. So, okay. So we have actually quite unclear title here, making the universe chiral again. What does it mean? In fact, if you find it clarifying, the clarifying title is the following. It's evaporating vortex solid liquid which possess superconductivity and superfluidity emerging due to strong magnetic fields. Okay, it's really strange, right? So first of all, it's made by the way, from nothing. So there is no matter here, no graphene at all. It has hexagonal structure, but it's nothing really. The transfer property should be dissipationless. That's why we have second link, because we studied together the dissipationless transport in semi-metals and so on. So it's very interesting from the other point of view. And it's not a misprint. It's superconductivity and superfluidity. It's not a misprint. It's due to magnetic. Yeah, and this is actually misprint. Due to magnetic field, right? And let's then make everything massless again. The question is, you can ask, of course, why again? And the answer is that, okay, why we make universe chiral again? And usually the best source about universe is the Hitchhiker Guide to the Galaxy of Douglas Adams. Here it's not the case. Here we should use Wikipedia. Not written by ChatGPT Alberto yet, but still it's our good classical Wikipedia, which says about chronology of universe. And it says that when we were young, all of us were young, like 1 picosecond young. Before that epoch, the matter was massless, basically. It was very hot. We had maybe magnetic fields, but the universe was massless. And you can see here there are worlds, therefore all fermions are massless before 1 picosecond. That's because Higgs did not get its mass yet. I mean, not physical Higgs, who is, I think, 90 kilograms, the big person, but I mean Higgs as particle. So it was before that epoch, things were massless, and in fact, we are kind of okay. The particles are massless, are massive right now. So that's okay. That's the point. So there were again before the universe has been had this massless phase, and the question is, can we do the same with magnetic fields? Okay, so the question is, can we do with magnetic fields? And I must say that, oh, that's actually PowerPoint, how it appears. So sorry for that, because I just converted my keyboard. I found actually the massless particles, they often appear in nature even today. And I found various fascinating forms of it. We can find it. For example, I found yesterday, because I was on the trip from France to Spain, or to Madrid, and we stopped close to Bilbao. And then we went yesterday from Bilbao to Madrid. And first of all, we found in Burgos, we found this kind of tree. There you can walk around the river and you can see this kind of trees. And you see it's chiral. It's clearly chiral. So in chiral, it means massless. So you are convinced that we have a massless physics here in Spain. Second one, next city actually quite close, just between the Burgos and Madrid, it's Salamanca. And in Salamanca, there is a very nice library here, you know, and here it's covered with so small shells. And you can see here that it has a really nice hexagonal structure, exactly as graphene. Perfect. So hexagonal structure, Dirac cones, massless particles. That's why we see in nature, we see handmade structures, actually this quite long ago, which are, okay, which show that we have some massless physics around. The second question is, okay, no, stop. It's just things which I don't actually, And this was first motivation. The second motivation is just to check from the first principle, numerical calculations, emergence of superconducting superfluid solid liquid phase generated due to vacuum instability by strong magnetic field. And it's actually, the next question will be, how strong should it be? And I must say that research is quite serious, because it's physical regulators last month. So it's something which we can actually test, and okay, it's something which I hope that exists. And people who do black holes, Adolfo, then you know that with black holes, we have also a big story about black holes. Unfortunately, I don't have 3 hours right now, I have much less, so I cannot talk too much, but there are also black holes here, a little bit. So, okay, so the question is how much really strong we should have the fields. In this famous review by Maria, I think you mentioned that the fields, the synthetic fields in graphene could reach like hundreds of Tesla, right? Like 500 Tesla, something like that. Hundreds, right? Okay, I need a little bit more. It's not like a pencil like this, you know, point like cat, which is lying there. I need a little bit more. It should be approximately, okay, let me say how more. It should be actually physical scale, yeah? So let me say, for humans, we are really actually very weak to generate fields, magnetic fields. We are kind of, I don't remember exactly, but I think like 10 to minus 12 Tesla, something like that, very, very small. Just when we think generate, our neurons generate fields. Let's start from Tesla. It's not a car, it's just a magnetic field. So it's just typical 1 Tesla, it's loudspeaker. Just basically what we have loudspeaker, maybe somewhere here, maybe loudspeaker here, we should have them. Then I will jump quickly to 10 to 9 Tesla, that's QED limit, that's Schwinger limit, which is mass of electron square divided by electron charge, it's 10 to 9. And that actually should exist at close to magnetized surfaces. It was, I think that there are right now examples where people think that such fields exist. And such fields are interesting because they can make a vacuum birefringent. It means that the vacuum with different polarization, lights with different polarization have different trajectories. So basically, they make kind of magnetic lengths made in the vacuum from nothing, just due to polarization of the vacuum. It looks like a bit like gravitational wave, like gravitational length, but it's not gravitational origin. It's just basically QED loops here. And they can exist at the surfaces. At core of magnetars, we can have higher fields, but they are actually not accessible to us. Okay. We need to have equation of state and so on. But in principle, 10 to 14 Tesla, that's really something which exists there. That's what we expect from there. Okay, I leave here some references where one can find about those magnetic lengths and why people discuss them and find them actually quite interesting and quite feasible in the universe. Another one, magnetic field, which is close to my field already, this is QCD scale. It's 10 to 16 Tesla. That's basically mass of proton square divided by electron charge. Those fields, they appear at the heavy ion collisions. So when you collide two ions and ions are charged, they create momentarily electric current. And this current is create magnetic fields because you can think that one ion moves in this direction, other ion moves in that direction, and between them you get quark-gluon plasma, and quark-gluon plasma gets some angular momentum, and it's just creating some magnetic field, and this magnetic field is 10 to 16 Tesla. And these two effects like magnetic catalysis, so we will discuss with Alberto probably at some point, magnetic catalysis, yeah, and also maybe vacuum superconductivity, but I will not touch this topic. For me, those fields are quite small. And they actually live for a very short time, for 10 to 24 seconds, so for 1 yoctosecond. Very short, I mean, nothing you can do with that. And then fields which are interesting for me is 10 to 20 Tesla. Those fields are electroweak scale. It's just mass of W boson square divided by E, electric charge. And there were discussions a long time ago, actually starting from basically from end of 3 years after this Franco time, as I understand from this talk, it's important to know. Yeah, so 1978, first time people mentioned that these fields may be important, and then started developed quite a lot with the works of Kharzeev and also Björn Olesen and others. So basically, such field could have existed here at early universe, and we are somewhere here right now. So they could exist at the universe, but people usually, when they don't understand why you need some very big fields, you say, okay, it can exist in, they're existing there, where things were strong, people were younger, and so on. So maybe many things may happen there. In reality, they also can exist right now. In principle, they can exist at a so-called highly magnetized black holes. So if you have black hole with some high magnetic field, imagine that black hole in the course of the universe swallowed a lot of magnetic charges, monopoles. They are inside, they have hairs, and those black holes can have this magnetic charge, and at the surface of the black hole, basically it's not the surface, it's actually horizon. At the horizon of the black hole, you may have strong magnetic field. And strong magnetic field at the horizon of black hole can produce the effects which I will be discussing later. This vortex, magnetized liquid fluid. And these are just pictures. I just very briefly flashed them. They were just showing that in principle, such magnetic fields here, the strong strengths of magnetic fields, and here are masses of black holes in the units of masses of the sun. In principle, those magnetic fields could have been created during the course of our universe, evolution of our universe, in principle. So in principle, they could they can exist also right now, somewhere. So in principle, this I'm talking about effects which can be existing today. And one of the people who turned attention to this subject was Juan Maldacena, who said that, okay, in principle, this actually pictures from his paper. So you can have some structures around black holes, which reminds corona. And I must say, this paper has been published during the coronavirus time, so it was right picture, right on money. Exactly when we should publish coronavirus with the help of black holes. Okay, so if you have strong magnetic field, many effects can happen. At QCD scale, there was suggestion that due to Rhombus and condensation, we can have vacuum superconductivity. I will not touch this right now, but there is another effect which is very similar to this one. If you have electric field of electroweak scale, very strong electric scale field, then this magnetic field can lead to W boson condensation. So I will discuss this very briefly. And this condensation can lead to the structure of the vacuum, which becomes inhomogeneous. So you have condensate in the vacuum, so you have no matter. It becomes inhomogeneous, and in a sense, people discussed it before, and they said, okay, it's kind of classical solutions, undisputable, easy, very simple in a sense, so it should be there. But then other people came and started to find it and could not find it at all. So our work is first who found the structure in the system. So let me show how system works. I will be very, very brief, just because it shouldn't be much science. I will show some videos later. So what's going on is very simple. So let's take a particle, free particle with spin, with some spin. So you have particle with some spin, and you calculate in magnetic field just Landau levels of this particle. Then, since particle is relativistic, so there is no interaction, you consider a relativistic spectrum, you can find solution. And solution is like that. So here is energy squared. It depends on the momentum along the direction of magnetic field. Magnetic field, of course, is homogeneous and static. So just magnetic field in one direction. So you have conserved momentum along axis of magnetic field to Vpz squared. You will have here mass, of course, because particle has some mass. And then between you will have this one. So this is EB, I take it always positive. So it's electric charge times magnetic field. And here we'll have some factor which normally encodes the structure of Landau levels. And what's important here that n here is a non-negative integer number, which labels Landau levels. And here is SZ, it's just projection of spin on the axis of magnetic field. And if, for example, SZ is equal to 0, then you get that magnetic field will always give rise to the scalar, to the mass of scalar particle. No problem. If you have S equal to 1/2, then you will get this lowest Landau level degeneracy, huge degeneracy, because the energy of particle would not depend on the magnetic field itself, because this number can be made 0. But if you have the particle with the spin 1, then you can find the state with projection equal to 1 to the axis of magnetic field. And then you will find that the lowest Landau level will actually feature this term. So we'll have some mass of your original particle. Here I put mass of W boson minus E times B, magnetic field. So it means that at some magnetic field, which is equal to square root of your mass, this magnetic mass will become 0. And then if you increase it a bit more, magnetic field, then mass will become imaginary. So the square root becomes negative. So it means that you will have some instability. And it means that your vacuum state is no more valid. So you have to have something new. And this is exactly the field I'm talking about. So vacuum should be unstable. And this instability means actually superconductivity. It was mentioned in one of my papers. Actually, I did not cite it here, maybe before. So the vacuum gets a condensate of W bosons due to magnetic field. So due to magnetic field, you get a condensation of W bosons. Then it becomes, since condensate charge, then it should be superconducting. You know that if you have charge condensate, it should superconduct. On the other hand, transverse motion of particles are not allowed because you are sitting at lowest Landau level, and you cannot jump between, so you cannot jump transversely, basically. So it means that superconductivity will be only in one direction. So it will be only along magnetic field. Okay. And here I briefly show that, okay, and then there is another thing that you can say, okay, right now I have, for example, this strange phase, which is featuring this instability. But if I consider really too high magnetic field, what then will happen? And then it turns out that there should be, theoretically, there should be second transition phase, which is equal to mass of the Higgs squared, which is higher than the mass of W boson. And here there should be symmetry restoration phase. And this symmetry restoration phase has been predicted a long time ago at 75, notable 75 year, by Salam and Stratsky. This is a Nobel Prize winner. And they got it right. They said, okay, there should be some new phase which should feature a total restoration of electroweak symmetry. So that's why we can make world Karl back again. Great, not great, but back. I mean, so we should have restoration of Karl symmetry here. Okay, not Karl symmetry, but okay, of masses basically, right? So particles should become masses here. And this work dated by 1975, and then Andrei Linde, who is famous for cosmology, also discussed this point later. And there were many different discussions what will happen here, and there is total ununderstanding. People not understanding what's going on. because we don't understand what's going with this phase. There are people who said that nothing is possible. Here will be some ordinary vacuum, nothing will change. There are a huge number of works. Then people come and just started to do numerical simulations and found that there is nothing. So, I mean, it was actually difficult to do. They did it with some long time ago, with 20 years ago, with some simplest models. And here, I very briefly just show that there is, so basically what we do, we just consider electrical Lagrangians, just typical electrical Lagrangian, which consists of W bosons, massive vector fields, Z boson, which is also massive neutral field. We have a usual photon, and we have a Higgs particle. So it's a very simple model. There are no fermions at all, because in this level, this is enough to discuss. So all other particles, we just contribute as loops. And then we right now would like to say what theory says to us. Now, again, we get the hexagonal structure. So if you apply a magnetic field, which is a little bit higher than electroweak critical magnetic field, then we get the W boson will create a kind of a condensate inside vacuum. So here we'll see some kind of vortices that appear from basically from nowhere. And here the condensate, which will kind of circumvent around those vortices, will be here. And you'll get also some currents which will be circulating. Also, Higgs condensate will get discrete a little bit. So you'll have also some hexagonal structure. And Z boson condensate will also appear. So it will have some kind of tooth-like structure, which are also arranged in kind of hexagonal, more complicated manner. And actually, it's interesting that since here we have a W boson condensate of charged particles, here we'll have Z boson condensate, which is a neutral particle. That's why you will have, in addition to superconductivity, you must have also superfluidity in this space. That's just basically theory can show you. And if you look more carefully to the structure, it was published like 10 years ago, you will see that if you look to this hexagonal structure, I mean, you just made a cut of your system, of your space perpendicular to magnetic field, you will see that there are many vortices around. So these dots are different types of vortices. These are charged vortices corresponding to W condensate, and the other vortices are neutral vortices which correspond to superfluid condensate. So you will have very complicated structure appearing basically from nothing. And let me just again say that this is a very simple model. It's extremely simple model, just electroweak model with correct Weinberg angle, correct masses, everything. Just apply and you get this very strange, unusual structure just from nowhere. And in addition, one can see the regions where you have, for example, the conductivity of superconductivity in some particular places will be enhanced, and in other places superfluidity will be enhanced. So vacuum become quite interesting, non-trivial thing. Okay, so, and this transition should be of second order, as usually happens in classical or semi-classical analysis. And then we did simulations. And here our simulations show that if you indeed, this is magnetic field in units of Higgs condensate. Here is actually Higgs condensate, which normalized to unity at zero temperature, or zero magnetic field, sorry. If you increase the strength of the magnetic field, then condensate just basically stays more or less constant, and then it starts to go down almost linearly, and then it becomes zero. So we really confirmed the existence of three phases: ordinary vacuum, kind of superconducting vacuum, or homogeneous vacuum, and symmetry restored vacuum during our numerical simulations. I must say that those simulations took us like 2.5 years. So it started before COVID, basically. So it just really was very difficult. I mean, we never expected that. We found that there should be some kind of deviations with theory, but they are kind of, instead of unity here, we have 0.7. Instead of theory predicts that the Salem theory and Linde, they predicted that there should be some transition here at mass of the Higgs. We found 0.99. So here it's everything is fine. But then you can ask, okay, fine, but how actually vacuum looks like? Because it should be homogeneous. And here I plot, say, Z fluxes. So basically flux, just I take, like in Abrikosa vortex, you just take it, you just look to your material and you see where vortices are located. You choose some quantity to characterize it. Here to characterize it, I choose the field of so-called Z flux. So it's just basically magnetic flux, but for one of the particles. And one can see that if you have magnetic field strength is very small, then there is nothing basically here. But once you stay in this region, you will see that the picture becomes quite interesting. So you have some inhomogeneities which look like basically like a vortex kind of lump structure here, right? And then if you increase magnetic field further, you will see that here this region here the vortices disappear, and again we have only quantum fluctuations basically, or thermal fluctations. Basically here quantum, because temperatures here is basically 0. So we see here the region where we have those vortices around. And if you look to that, I don't know how to put it correctly. Let me just try. I never use it normally. So that looks like this. Let me just try to do that. So that's here we increase the value of magnetic field. So this magnetic field is increasing. And here I show the picture how a vacuum looks like. So basically we do photographs of vacuum just every time, and I make some smoothing between them. Now you cross into the region, you see, and here you see some vortices appearing. So they're kind of jumping together. And by the way, size of the vortex 10 to minus 18 meter. It's quite small actually. Yeah. So yeah, so 1 attometer. So here at 1 attometer, those are jumping around, right? And then we increase. We are coming to this restored phase, and we see second transition. And then again, we have restored phase, vortices disappear. So we clearly see the picture which had been predicted a long time ago, with one exception that actually it's not. Oh yeah, I can probably move further. Yeah, with one exception that it's actually not the structure which you would expect to see. You'd expect it to see some hexagonal structure. Here we see no hexagonal structure at all. We see it's not like a solid. On the other hand, it's not like a liquid, because if you look carefully, you will see that each vortex kind of has been fluctuating inside its own cell. So there was no kind of exchange between the vortices around. This looks like a little bit like a polymer, but kind of structured polymer. So it's not a liquid, it's not a solid, it's like disordered solid, something between them. Moreover, the solid appears from the vacuum due to magnetic field, and then it gets evaporated. So we have evaporation of nothing from the vacuum, okay? And here how it looks like, if you just visualize one of those configurations. Let me try to make it, because, okay, I tried. That's how it looks like. These are just vortices, some of the condensates again, how they look like. So you see that it looks like they're more or less solid, but it's not actually solid. They're not intertwining, but they are, yeah, they look like, yeah, and these are magnetic fields here, right? So we see the condensates, we see the superconducting condensate, we see superfluid condensate, which form this kind of like irregular structure, which is surviving in magnetic field and which do exist there. Okay. Oh, now it starts. So let me say that this is basically conclusions of my talk. I would like to say that we can make from nothing from the vacuum, from quantum fluctuations, we can make the solid, which is not actually solid, but it looks like more a liquid, which can be created, which can be evaporated. It's made of vortices, and it actually makes our universe, at least the part of universe, chiral again, because, for example, if you look too close to the black holes at some smaller regions, actually for the size of Earth, or say 1/3 of Earth, the size of that black hole should be some kind of centimeter type of size, and this region should be 1 millimeter. So it's quite pretty human, up to magnetic fields, of course, will be quite strong. So yeah, so that's a talk, and it's also hexagonal, a little bit like this, but flat. And I must say that this talk, I wanted to make a completely different talk about a different topic. It has been prepared, but then my wife, who is also sharing the same passion as Maria, she's a painter. She likes painting. And at some point she said that I said, okay, I'm doing something already a long time, already second month, and I have to change here. I said, but I mean, picture is perfect. It's really perfect. And she said, no, I have to change the here, there, a little bit there. So I just, oh yeah, that's how passionate people work. So when this material has been ready, it's also science. I hope that I brought it. I found that it's actually vortex. It looks like vortex, but it's another natural vortex made of the tree. Do you see vortex here? It's not hexagonal, but it's kind of realistic, right? So that's for you, Maria. Thank you.
Hey, thank you, Maxim, for this very fascinating talk. Are there any questions to how to get the hexagonal lattice from nothing?
I didn't quite get what's the direction of the magnetic field. So you're thinking about a black hole that gives you the magnetic field?
Yeah, exactly. Because you see, black hole actually at this scale it's big. It's not like atoms, the universe is big, very big, and unmanageably big. No, it's actually big, it's 1 centimeter. But here we talk about the scales about 1 attometer. So you see the size of the vortex is 1 attometer. So it's basically flat space for the vortex. So you have basically many vortex lines. Okay, you have many magnetic field lines coming from the black hole. And at this scale, with 1 attometer scale, it looks like extremely flat. It's to the edge of universe flat. And then you have many vortices there appearing. And those vortices will be, of course, fluctuating, as I have shown here, due to quantum fluctuations. It's like a monopole. Imagine that you have monopole with a multi-magnetic charge. And the charge, actually, if I can come back, the charge should be quite huge. Let me come back. Okay, it's here. So that's basically the charge. Okay, the charge should be really big, like 10 to 20 something. Okay, we don't know whether they exist. People say that black holes could not exist of such size. They should evaporate. Very much depends on the structure, exactly which region you have here. One of the regions can exist or cannot exist, where you sit here. There are many discussions. For example, magnetic field can evaporate black hole much faster. For example, if you take black hole of the size of the mountain, it could exist, if you take a Schwarzschild solution, it could exist till the end of the universe due to Hawking radiation, which will be very small, so nothing. But if you have it magnetic, and if you have it magnetic of particular range, then it will operate very fast, within microseconds. Just because of magnetic fields creates many chiral modes, by the way. And those chiral modes, which are light modes, will be just going back and forth close to the horizon, and will just enhance evaporation by the numerical factor, just by degeneracy factor, because lowest Landau level is degenerate. So magnetic field make evaporate magnetic black hole die faster. But it very much depends on the range. On the other hand, if magnetic field is different, a little bit of charge of black hole is different, then it can be magnetic, living long time, and just with real hair, you see, because it will be real hair. Actually, we want to make construction of the real hair. You see, you have black hole with many vortices like this, with corona. It should exist in principle. So yeah. So.
Yes, I have a few questions on this Higgs condensate. I would like to ask, this is an interacting condensate?
Yes. It's really interacting model. So we took really honest model. Let me say this completely honest model. Here there is somewhere inside there should be theta angle. It's basically the relation between this G prime. So we took everything from particle data group.
Okay, and in modern quantum gases, it's very common to use the contact approximation, which is reasonable in that context. Yeah. But I wonder, in this case, probably that approximation would not work. You have to put the gauge fields explicitly and so on. You see, it's actually contact in the sense that we have lambda to the 4th, so lambda phi to the 4th. Actually, that looks very much like a contact thing.
Yeah, it's contact, it's under term. It's just it's related to normalizability of the theory. So it's
very much like in quantum gases, because it's
you have contact attractive here interaction, right?
And then my question is, the elementary excitations of that condensate are the usual particles?
Okay, this is just Higgs particle which has been observed at LHC.
No,
yes.
No. I mean, in the condensate, probably you have many Higgs particles. I'm asking about the elementary excitations of that. That is the Higgs.
So, This are
the equivalent of the volume of modes. Let's see what is.
Normally we interpret them as here they're written. So these are just W boson, Z boson, photon, and phi Higgs particle. Higgs particle basically the charged condensate, and then they have Goldstone mode, which has been shown in a recent nice talk before me. Just Paco, I think, have shown this picture, right? And then you have Goldstone mode, but in our case, Goldstone mode is dead because it's eaten by W's, and W is becoming massive. This is just mechanism how.
So the Higgs particle is one of the elementary excitations.
Yes. There should be kind of more, but this is kind of our dream to find them, because the people discuss about extensions of the theory. Actually, this theory is not 100% self-consistent, but it appears at higher scales. So right now it works perfectly, unfortunately.
And can you have collective modes with that? For instance, in the case of Higgs, since it's a boson, can you have modes in which there is a macroscopic occasion?
That's bring us to previous talk about how lattice fluctuates. We had to talk about membranes, but here, if you look to this picture, for example, where we put magnetic field, here you will have those vortices. Those vortices can fluctuate, and then we'll have those I think Tkachenko modes and other modes, which are you have two types of Goldstone modes, and you can describe them. This will have. So you have the k to the 4th dispersion relation and k squared dispersion relations, right? So you can have them.
Thank you.
Okay, so if there are no further questions,
Yeah.
let's thank Maxim. Okay, so our next speaker is Luis Ibañez.
Let me thank first the organizers for inviting me, having the privilege to celebrate Geli, a good old friend of mine. Okay, in the beginning of time, images got frozen. Now it is frozen. What?
That's because of magnetic field.
Yeah. Yeah. In the beginning of time was Universidad Complutense. That was, and many of us started there, and Geli did in those years. It was a busy place those days, and we were all young and happy. We were by we mean the people who in the end turned out to be particle theorists and experimentalists. He was a bit younger than us. And well, I think already Paco showed this picture of the promotion of the group of Geli. I don't know, you're this, right? And Paco's over there. There's Arturo, many known people, at least to many of us. But she joined this was a small particle theory group at the Junta de Energía Nuclear. I was also working there doing my decina. I think I met you there, probably, no? Those times. And we were young members of a fastly growing community of particle theorists in Spain. This picture is a classic again, contains many information of the history of particle physics in Spain. This is the 5th International Winter Meeting on Fundamental Physics in the year 77. So by now it has been organized 51 times. Every year has been organized a very old scientific meeting in Spain. There are many well-known people, both Spaniards and people from outside, some prominent physicists. And here there is in this little group you can see, Geli. This is myself with a lot of hair. And okay, was in times. Look at this. This is also another classic. This was a wedding, you can see. Nice Geli over there. A gentleman who became a rector of the university. Again, I am there with her and Carmen and 79. But still, the options for doing PhD were not great in those days. Those days were a bit obscure, I must say. And Geli moved to Israel to the group of Aharon Davidson, and I started to work in things like cosmology, domain walls, extra dimensions. That gives me an excuse for my incoming talk, because you already started. You have scenes in your consciousness, and did the thesis in the Weizmann, and but then back to Madrid, and also in Princeton, the Institute of Advanced Study. You move to string theory. Don't forget that. Boson strings, string vertex operators, quantum gravity, with well-known collaborators also. But then in '92 came a phase transition inheritance. This was written for Keynote in Mac, like everybody should use. And now it should be some rotating transparency that will come. You are going to miss that. And current to field theories in condensed matter. And I think Paco also had to do something with that. And well, so since you have seen in the past, let me bring you back after 30 years to particle physics, string theory, and extra dimension, where you once belonged. So what I'm going to tell has not much to do in common with the previous talks. The only thing I have found in common is Dirac, the word Dirac. I'm going to discuss briefly some ideas of how Dirac neutrinos could play a key role in the origin of the the structure of fundamental scales in physics via an upside-down view of the fundamental scales in physics. When I say Dirac, it's in contrast to Majorana. What will be crucial in here is that a Dirac fermion in 4 dimensions has 4 degrees of freedom, whereas Majorana has 2. That's not to be crucial for what I'm going to say. So you know that I love all books. This is one of the books in my library. It's a very small book. This is Tosen Tan. So Danse de Mort, Danza de los Muertos, was something very fashionable for many centuries. And it's the idea that, you know, death treats equally the emperor and the peasant, and in the end, all ends the same for everybody. And it has very sinister pictures, which I can show you. I forgot to bring the book, by the way. But the thing which is interesting in this book, which is a small book, is that at the end, there is this picture. This picture is a gentleman with a crown of pearls, handsome, brilliant, and important man. And then they came the effect of keynote, and then you rotate this image 180 degrees, and you find this. It's the same thing. You rotate it, and you see this. So the pearls are now the teeth of this monster, and the hair are now flames. So depending on how you look at the thing, something which is beautiful can look horrible or vice versa, right? I love this picture. When I saw it in this book, I immediately bought it. Very cheap, very cheap. So I'm going to say that the fundamental scale, the way we normally talk about them in physics, is looks ugly if seen from the top down, which is what normally we do. What do I mean by this? Well, this is the scales in fundamental physics. I talk about these big scales. And this is the structure. We have only a couple of guys who are massless, photon and graviton. Then there is this other scale, 10 to the minus 11 GeV, in which some interesting things happen. There is that's the overall scale of neutrinos. We don't know, in fact, if neutrinos are Dirac, 4 degrees of freedom, or Majorana, 2 degrees of freedom. And in fact, we don't know even if one of the neutrinos could even be massless, one of them, not more. And there is another thing in the same scale of energies, which is the cosmological constant. This is the vacuum energy in the universe, dark energy, which dimension 4. That's why there is 1/4 over here. So, which would explain the acceleration of the universe. And by some unknown coincidence, or maybe not a coincidence, they turn out to be similar. Then 11 orders of magnitude or so comes this region, the electroweak scale that our previous speaker was talking about, lambda QCD, and the latest guy in this bulk of particles and things is the electron. And well, in an amazing triumph of experimental physics, it was found 10 years ago as an interesting mass, 135 GeV, looking like an elementary, not a composite particle. And finally, there is, we expect, because the theory looks incomplete, it should be some ultraviolet completion, which seems to be close to the scale of quantum gravity, which MP, the Planck scale. So there is essentially, apart from the zero mass, there is essentially 3 blocks of masses, which are separated by 12 orders of magnitude. And it is a fact that we don't understand why. What is this separation? And there is this unexplained huge hierarchies between the 3 blocks of scales. But commonly, I mean, for a particle theory, typically would tell you, eventually, in the in the completeness of time, we will be able to compute, at least in principle, different things in practice, these fundamental scales, the cosmological constant, the Leftowi scale, if there is a unification of string scale, in terms of some fundamental, very, very high energy scale. But this is problematic. For example, to compute the energy of the vacuum involves, for example, you compute a loop, you should include even non-perturbative effects. It's something which is very difficult to avoid, that if you do such a computation, the result is going to be of order of the higher scale. This is the typical hierarchy of scales, and which happens also for the scale of the Leftowi scale. I mean, you do a loop, and in physics, normally, that's what you teach to your students. Parameters take essentially the maximum value compatible with the symmetries. That's what the loop corrections or quantum corrections do for you. So you need to do some tremendous fine-tuning. The theory somehow should appear some terrible fine-tuning to understand that. So the situation is a bit like this. By the way, I'm using a confusing notation. The cosmological constant V naught, so the vacuum energy of the potential. I'm going to use the three of them in different places, but they are the same thing. But there is this upside down idea that I want to mention here, which is a bit, looks from a particle theorist point of view, a bit strange, because what it says, well, maybe after all, what is fundamental is really the opposite way around, the cosmological constant, the energy of the universe. And the rest, the higher scales, neutrino masses, electroweak, are maybe obtained in terms of this tiny thing, which is something very small, and maybe by powers or in some way. This would be very satisfactory because if you do a small perturbation lambda, you multiply by 2, the higher scale practically do not move. So there is no instability in some way. Well, from the point of view of particle theory, it looks crazy because we all have always thought that the cosmological constant is the result of summing all the contribution of all particles to the vacuum. No? Here it would be the same opposite. You say, no, it is an external parameter. And from there, you have to build up the rest of the quantities. What I'm going to say is totally speculative, but you know, physics is fun. So yeah, and good ideas start with a speculation, and then you have to fill the details. There's a few key ideas which have been turned out to be recently has been given special support. The first point is that we have realized that putting a normal field theory inside the consistent theory of quantum gravity implies constraints on low energy physics, which go beyond just the presence of Planck superoperators. There is some ultraviolet infrared connection. There is something non-trivial there. It's not something that you add like a perturbation. It's some bigger effect. Examples of strange things happening in the presence of quantum gravity is the following: the so-called magnetic weak gravity conjecture for a UAM, which is the following thing. In a theory consistent with quantum gravity, you have a UAM gauge theory like electromagnetism. First, the gauge coupling constant is in fact a field. That seems to be a general property in quantum gravity. So it is the bed of that guy which fixes what we see experimentally. Now, the point is that in the theory, you go to 0, that limit, which is the limit all physicists like, and you tell to your students, good look, when your coupling is small, it's great because you do perturbation theory and you are done. Doesn't work in the presence of quantum gravity because when it goes to 0, the situation is singular. Essentially, what is hidden there is that when G goes to 0 in an effective manner, you're recovering the global symmetry. Global symmetries are forbidden in quantum gravity. That's what is hidden there. But in practice, what happens is that there are bounds like this that are in the presence of gravity. This is the Planck scale. This is the coupling constant, gauge coupling constant. If you make this tend to 0, in your spectrum is going to appear towers of particles, huge number of particles. Typically, what appears is just a tower of Kaluza-Klein particles, or some cases, full string theory. That's what seems to happen. So it's not a normal limit. The second point to emphasize is that those towers may have an effect and do have an effect at low energies. One of the effects is that the fundamental scale of quantum gravity is lowered. It's not the quantity that Planck computed. It gets reduced in some way by something trivial, renormalization. If there is a huge number of particles, then the kinetic theorem of the gravity and the Einstein's action is corrected, and it may be corrected. In fact, it's corrected in this way. It is lower by n, but n may be huge. N may be huge. So the quantum gravity scale could be maybe above LHC. It's not what I think is happening, but I mean, depends if you have this tower, because there is some field or gauge coupling which is going to 0, then the quantum gravity scale is lower down. And in fact, one can see that a connection of this form appear, sort of which connects the theory, the scale at which quantum gravity becomes crucial to the lightest state in the tower, which is going down, which is in general, since this is low, much below what you would expect the Planck scale. A second effect of such towers is that there may be huge wave function renormalization for your fields. Again, the same story. There is a lot of stuff going on here for a fermion. It could be, for example, I'm going to discuss the case of right-handed neutrinos, may get a huge, which in fact, when you put numbers, you may get an enhancement for the wave function of m Planck over the value of the tower. If the tower is 10 orders of magnitude below, then the wave function gets a huge factor. So this is an example of two effects which may appear. It works as a pointer. So I need to. Okay. And then if you want to apply to the observable world, it may have an effect on matters, on lepton quark masses, which make the standard model. In the standard model, the masses come from the famous Higgs bed, which I'm going to call M electroweak, and through the Yukawa couplings in this way. So the mass of a fermion, whatever fermion, QR, lepton, whatever, is a coupling constant, which is a Yukawa coupling times the Web of the Higgs. Okay, but the physical Yukawa coupling, in fact, gets also the wave function renormalization, wave function normalization of your fields in the Yukawa coupling. The Yukawa coupling is a coupling of a Higgs to a left-handed fermion and a right-handed fermion. And then there is a minus here. You get a huge reduction. So towers may generate hierarchies of masses due to this wave function redefinition, and could be the origin of the tiny neutrino masses. So, for example, for the neutrino masses, which are given by Yukawa times Web, that's if the wave function renormalization or redefinition or your right-handed neutrino is very, very small, then you could fit the observed value of the massive neutrino, which is of order 10 to the minus 1, 10 to the minus 2 electron volts. So you get an expression like that. You don't expect huge renormalization effect for the Higgs and the left-handed neutrinos because they couple to because we see that the masses they have, the electron is a large mass, but not hugely small, okay? So that's why I have only put one wave function factor here. So if you want to describe the value of the observed value of the neutrino masses, this tower should have a mass of order around 700 TeV. So not accessible to LHC, and not even to FCC. Anyway, these are objects which are not charged under the standard model, so you wouldn't be observable at LHC either. Anyway, this means that to describe this, you need an extra dimension opening at this kind of scale if you want to reproduce those neutrino masses. But then this gives you the scale of the tower, which is, I call it also for adding confusion, MKK, Kaluza-Klein. Now, from the previous expression relating the mass of the tower to the scale of quantum gravity, you compute for this to work, the quantum gravity scale is 10 to the 14 GeV, just slightly below the usual scale which is taken from the grand unification, which is 10 to the 6, but it is lower. So the fundamental scale is lower. Okay, so how this could help with the story of the scales in physics? Here comes the contact, here comes Dirac, and here comes this coincidence word I was mentioning between the value of the vacuum energy in the universe and the scale of neutrino masses, which is, there is no obvious way to understand it. It looks like a coincidence. Maybe it's a coincidence. I'm going to claim that maybe it's not a coincidence. There is some arguments by Auguri and Baffa, which give rise to something called the ADS de Sitter, non-Susy conjecture, which is negative energy vacuum inconsistent in quantum gravity. You cannot construct a consistent theory of quantum gravity around formally vacuum of this structure. I'm not going to say from where they extracted this conjecture. It's based on string theory samples. And the idea here is, imagine taking a standard model and you reduce it in a circle. A circle compactification is sort of trivial. So if your theory in 4 dimensions is consistent, your theory obtained through a circle should be consistent. Now, what you find if you focus in your lightest degrees of freedom after doing this compactification, which is just taking one of the space dimensions and formally taking it to this, by the way, this doesn't want to describe the universe. It's telling what we are going to use is that you have the standard model, which is clearly consistent with quantum gravity because it's there. And then you reduce it in 3 dimensions. You should obtain something consistent. Now, if you focus in the latest states in the theory, you have the photon, the graviton. So this is 2 bosonic degrees of freedom, the graviton, 2 bosonic degrees of freedom. And then you have the neutrinos. And okay, there is a Casimir energy. There is a Casimir balance. These are bosonic and give rise to the tend to not allow that the theory is reduced to 3 dimensions. Neutrinos, because they are fermions, they depend on the boundary conditions, but I'm not going to enter into technicalities, have the opposite effect. And something like this happened. If the latest neutrino is Dirac, which I recall you, there was a neutrino which we don't know if it's even mass. We don't know its mass, so we can play with its mass. It's a free parameter in the theory. So let us consider this latest neutrino. It has 4 degrees of freedom. That's great because it matches with the bosonic degrees of freedom which exist: 2 photons, 2 gravitons, 4. And that when you compute the Casimir energy, you don't get any minimum. You want to avoid this minima, according to Auguri and Baffa, that leads to consistent vacuum. Now, if the neutrinos were Majorana, only 2 fermionic degrees of freedom is not sufficient to avoid the presence of the minima. So why Dirac neutrinos are important here? Now, the point is that you avoid the minima if you just compute the effective potential. If the neutrino, the latest neutrino, is below the cosmological constant in 4 dimensions. There is a term in the 3-dimensional action which you inherit from the 4-dimensional action for the third cosmological constant. So you get this interesting condition. It's interesting because of two reasons. First, it gives an explanation of this coincidence, why the neutrino scale is of order the cosmological constant. Secondly, it gives you an interesting bound, which is going to help us with the scales. This is the constraint that you get between then the Kaluza-Klein scale, which is important in computing the Yukawa coupling of the neutrino and the Higgs path. So we have seen that this Kaluza-Klein scale should be around 10 to the 6. And then this bound, we have just found that this region is forbidden, okay? Tells me that the Higgs web cannot grow farther than that. So it implies the stability of the electroweak scale. It cannot, that's the hierarchy problem for the electroweak case, is that the loop, the quantum effects, will tend to give a huge web to the Higgs. That's not possible here due to this bound. And in fact, specifically, just using the previous formula tells you that the electroweak scale is given, is maybe written in terms of the vacuum energy of the universe and the mass of this extra dimension. So at the end of the day, what happens is the following, is that all scales may be written, all fundamental scales may be written in terms of the cosmological constant, the energy of the universe. The neutrino masses are of that order, if that bound I showed you is correct. The electroweak scale, when you put numbers, go like the power to the 1/8. And well, if you have a supersymmetric version of the same thing, you get a similar scale for the Susy breaking scale, but that's optional. You don't need supersymmetry to solve the hierarchy problem here. You don't need it, but it may be needed for other purposes, which I'm not going to discuss. For example, the value of the Higgs 125 GeV smells supersymmetry totally, but it's not solving the hierarchy problem here. And the fundamental scale, as I told you, is 10 to the 14 GeV, but it is particularly this power of V0. So all scales are depend on this boundary condition of the universe, which is the cosmological constant, the scale. This is quite insensitive to V0, of course, because if you multiply V0 by 2, you get who cares if the unification scale instead of this is 2 to the 1 to 24, which is practically 1. It's really stable, and there's small changes of the cosmological constant. There's no fine tuning in here. And another peculiar thing which happens is that if the cosmological constant goes to 0, everything goes to 0. So all the universe, all the history of would collapse to 0 energy because it goes down with this power. So all physics scales will go to 0. Now fortunately, we are in a situation in which V0 is what it is and allows the separation of scales. There is life. So you have the electroweak scale around what it is, thanks to the value of V0. But if V0 was smaller, we would be here and we need no physics, essentially, because you cannot reproduce what we observe in the universe in this situation. So now, but look at this mystery. How comes that V0 could be fundamental? In what sense? Just the vacuum energy. I repeat, for a particle theory, particularly strange, because for a cosmologist or a relativist, no. People working on relativity, for them, what is important is the curvature, is precisely this. These are the fundamental parameters. For particle theories, this is the opposite. The cosmological constant is what we compute doing Feynman diagrams. Particle theories, in some way, we will be wrong, and we should have taken more seriously the cosmological constant as an external parameter. And how could be that? So V0, well, Planck scale is still there, are the fundamental scales. But how and why? Why it should have any particular meaning? A possible guess, which perhaps I think it was Tom Banks the first, but after that also Susskind has thought in this kind of things, is the following, that we know that we live in a world with positive cosmological constants, or the zeta geometry. Gibbons and Hawking showed that there is a notion of entropy associated to such kind of gravitational background, which precisely goes like this, like the inverse of the de Sitter curvature of the vacuum energy. In our case, if you interpret the vacuum energy, well, this is the positive curvature of de Sitter. So entropy of the universe. It's clear that the observed universe, entropy in what sense? Well, degrees of freedom. And the universe we observe has a huge number of degrees of freedom, really huge. But that's consistent with the fact that the cosmological constant we see is tremendously small, ridiculously small. So the idea would be that the cosmological constant is so small because we need to have sufficient entropy to be able to describe all the degrees of freedom in the universe. So the universe will have an entropy budget. You have a universe, you have possible entropies, which are given by the de Sitter curvature, but that's an input. And then the universe evolves as it would, as it may, as well as it could. And if you reach a certain region, the values of the cosmological constant are simple possible external boundary conditions. And there are, some of them are viable, others are not viable. Fortunately, we are in a value which is viable. This is no anthropic. This is just a fact that there are solutions which describe what we see in our solution, which do not describe what we see. Okay, so we have to think. I think this is a promising way to. It's not obvious. How do you find entropy of the universe? How do you compute it? What is the entropy inside all the black holes of the universe? It's more a formal explanation than an actual explanation. But maybe eventually, if we are able to do such a computation and it matches the cosmological constant, it would be great. But even simply taking it for granted, and you are a cosmologist and say, no, I take seriously cosmological constant, going from the bottom to the up, seems like a logic possibility to avoid fine-tunings. And in fact, it's supported by some arguments based on quantum gravity. So I was just trying to convince you that this universe, which is ugly, we try to see it in the traditional way, describe it from the top bottom, looks better if you look it upside down. And congratulations on a distinguished career, Kelly. And we hope to be in this shape the rest of our lives. And please keep on enjoying life with your friends. Thank you.
Okay, so it's a very interesting talk with new perspectives on fundamental physics. I guess there are many questions.
You have many questions, but you can ask them in the IFT.
Yeah, I can ask you privately.
But no, also publicly.
Publicly as well.
Privately, one question, cosmological constant can in principle evolve with time.
Yes.
So your particle masses can also evolve with time. And we have some stringent constraints on the particle masses. Alpha is constrained.
Correct.
How this theory is constrained with this direction? It's constrained with this.
I don't really know. I haven't studied, or nobody has studied the cosmology of this idea, but it's true. Imagine that it's true that there will be constraints, because if all the scales depend on time, there are strong constraints on that. You cannot. So it depends much on the speed of the variation. If there is also if there is or not something like quintessence. I don't know. It's I don't have any more clever answer than that. Yeah.
Hi, Luis. I understood that it's essential that the neutrinos are Dirac. So if
just because of the number of degrees of freedom. So you have two Majorana, it's okay also.
Okay. Okay. So I mean, there's experiments that are going on to try to see if there is neutrinoless double beta decay.
Bad luck for them.
They should not find anything.
They shouldn't find anything.
Okay, that's
And
good
in fact,
because that
if
makes
you
you
put
falsifiable in a
Sure.
in a very recent
Some of the arguments are
perspective.
sure.
Very good, very good.
Put some water on this. You might have sterile Majorana. You're just counting degrees of freedom, right?
Yes.
Yeah. So
Yes,
if you
yeah.
have sterile
But for
Majorana,
me, I don't see any distinction between a vial fermion and a Majorana. What counts is the number of degrees of freedom. It's the two different ways of writing the same thing. For me, what is so there is not a thing. I don't see a distinction. It's just so you need 4 degrees of freedom just to match the two elicities of photons in there.
And there's also no between that.
Well, there is a possible difference. If a real Dirac has a single mass, 2 Majoranas can have, so there is something called quasi-Dirac. There are quasi-Dirac fermions. That could also work. So if they are not very separate in mass, that could also work. Dirac or quasi-Dirac.
okay, so Geli, I think we have to do this in semi metals, right? Yeah. Okay, thank you all, especially the speakers. This is Maria Pilar Lopez Sancho, and she will tell us about topology and disorder.
Este mentirijilla. The title. Well, first of all, I want to thank the organizers for this compulsory event, especially Belén Valenzuela, and I really appreciate to be invited. Well, this talk is dedicated for Maria Ángeles Bodmediano. We knew her as La Bodmediano when we were at the university, and it is to thank her work and celebrate her success. And I only want to remember the work we have done together and to underline the importance of her role in my research. So my talk will be very sui generis. I have only occasion of listening to the last two, and well, I think my talk is different, and maybe it's out of place, I don't know. Bueno, que esto no puede ser. Well, some people have commented before me, we met in other centuries, in concrete in the 20th century. And as you see, that was only black and white, but a lot of future, as we see in our faces. And this is the future, the reality now. We formed the quantum field theory group with Belén Valenzuela, and Maria is the boss. This group is now small and doesn't fulfill the parity requirements of the European research area. But in other time was big and diverse, but it undergone a very complex evolution. The male members dispersed in a kind of male decay, and we arrived to this core of 3 members violating the parity. And we started to collaborate in this century, and we in a project directed by Paco, who was the gluon of the team at that time, and we started to study layered metals. I remember that Geli produced this graph with a very new tool then, Mathematica. She was very proud, and really I admire her from the bottom of my heart, because she arrived to this graphic. And I was also very happy because I wish to have a Feynman diagram in a paper, and we have this, although it's the lowest contribution to the self-energy, but it is a Feynman diagram. And then we was studying always with Paco and Geli non-trivial properties, but in the clean limit. And then graphene was done, and we started to consider the lattice of graphene. And Paco, no mercy, make a big hole in the lattice. Geli and I always refer to this paper as El Roto, because, and we study with Tobias, a German physicist. We study the effects of the broken bonds with an electron-electron interactions. And you know that Maria always combined the generation of knowledge with the dissemination of the knowledge. And then we went in a scientific mission to contact experimentalists to Brasilia. We learned a lot in this scientific mission. And we refined the way of manipulating the lattice, and instead of a broke, we start to induce defects, topological defects. And we count with Fernando de Juan, who was a student of Geli, which besides to be a magnificent physicist, was a very good musician as well. And well, this was a very nice paper. We learned a lot in working in it, and guided by Maria. And we mastered then the way to produce vacancies. And Eduardo came from Porto. I think he was attracted by the potential well of Paco, which is a very strong potential well, but Maria invited him to collaborate with us. And to begin with, we add another layer so that we have more playground to induce vacancies. We start with the bilayer, and you see in his eyes that he has, as a good Portuguese, this eagerness of expanding. You can observe here that he has 3 numbers for the affiliations, but he has only 2 affiliations. But well, this was his launch. We studied that with Harty Fogg, this famous couple that I like a lot. And with these refining methods, with the help of Eduardo, we arrived to a new type of vacancy. This was really very important. And we enjoy a lot with these works. But Maria Bodmediano, you know, likes to be in the forefront of the fashion. So she made us to leap forward. And he took us from our comfort zone. And then we take the Haldane model. We introduce the complex hoppings. I remember that I bought a 2-color pencil to see the faces. And besides the vacancies, we start to introduce Anderson disorder. And we learn to calculate the Chern number. It's the first time I saw him without Simons. And we calculated the whole conductivity, the localization length, level statistics. And it was then with this level spacing that I acknowledged the important work of Wigner. I knew Wigner because besides to be the brother-in-law of Dirac, which for me is a milestone, he received the Nobel Prize with Maria Gepper and Jensen. And this slide I have shown a lot because Maria with Marie Curie were the only 2 women Nobel laureates for years. But studying this work, I understood the importance of his contribution not only to the theory of atomic nucleus and elementary particles, but also to many other branches of the physics, in fact, to the condensed matter physics and other more. Well, with all these tools, we start to study the effects of the Anderson disorder on the topological states, on these states who carry the index, the Chern index. And we discovered a very fascinating process, the levitation and pair annihilation. And I advise you to read about because it's really fascinating. And in the eagerness of Maria to have this parity in the authorships, she recruited another collaborator, who was Raphael de Gale, a French collaborator, with a deep physical intuition. So we continue expanding our work. And this here, which is a very strange slide, because I have always liked the hairstyle of Poisson. And since we were studying the Poisson distribution, I decided to put an image of Poisson. But then, thinking on Eduardo, I looked for a Portuguese physicist, and the first one I found was this, which is related with Tintin. I don't know why. Tintin, it seems that goes to ask for some physics question to this Señor Pedro Joao dos Santos. We continue expanding our work, and with Raphael de Gale and under the guidance of Maria, we considered other lattices with different symmetries just to see what was important in the phase transitions to arrive to a topological state. And this is the last scientific mission we were able to do, always with experimentalists, you know, because it's very important for our work. And well, I would like to thank all the collaborators. Eduardo is delocalized, completely delocalized now, but from time to time we can find some moment to collaborate, and the others are abroad. I thank as well to those who ran away and abandoned us, because, well, it's the life. But the most important thing I wanted to express here is my gratitude, my acknowledgement to the work of Maria in this institute. We have discussed a lot in her blackboard. I look that now they say whiteboard, but she has a blackboard. And I really have enriched my knowledge, and I enjoy a lot working with all these people. Well, you know that I am not gifted for the art, so te invitaré a un bocadillo de calamares, y muchas gracias, colega.
Yes, I can.
Hi, Dima. Good morning.
Hi. Good afternoon.
How are you? Okay, so can you confirm that you can see us?
Yes, I can.
Great. Good.
Wonderful. So thank you so much. It's a real pleasure and honor for me to be with you today, if only virtually, on this remarkable occasion to celebrate together with Maria and all of you. So Maria is really one of pioneers of the interface between condensed matter and high energy physics. She's been an inspiration both for me and for many other physicists. And you know, I'm truly honored to be one of her collaborators. So this is Maria during one of her visits to Stony Brook, at Simon Center, and every meeting with her, it's a real delight. And Maria is talented in everything she does, and I'm as big fan of her art as of her physics. And in fact, when I think of a happy retirement, nothing captures it better for me then this painting of a sunlit terrace, with family and, children and grandchildren. And, this is, to me, how the happy retirement should look like. And, Maria really captured it here. So I also greatly enjoyed my most recent visit to Madrid when Maria showed me some of her favorite places, and some were immediately and obviously beautiful, and we saw some great art, and some places were beautiful in less obvious ways, like this M30 highway. But when you look at it for a while, you kind of start to get the dynamism and energy of this site, and I'm going to use it later in my talk. And after that, we had really great evening and quiet, long conversation with Maria and Ángel in the beautiful apartment, with a great view of Madrid. And in fact, I would rather, continue looking at Maria's art than coming to my own physics, because I enjoy her art more than my physics. But since I promised to the organizers that I will say something, so let me come to the physics part of the talk. So I'm going to discuss three related topics. So all of them have to do with quantum entanglement and chiral matter. So the first one is quantum entanglement in production of fermion pairs. The second is effect of confinement or charge screening on quantum entanglement in the production of fermion pairs. So here I will show recent results of a quantum simulation. And the third will move closer to condensed matter physics. And, I will briefly discuss how to use entanglement as a probe of phase transitions. So let me come to the first topic. I promise it will, I will be quite fast, so you will not see too many equations in this talk. I will just focus on underlying ideas. So let's first talk about the production of fermion pairs, so the Swinger process. So here you produce a pair of electron and positron in a pulse of an external electric field. And then this fermion pair is produced, and then they part their ways, just like in this image of M30 highway captured by Maria. But as they part their ways and stay out of causal contact, they actually remain entangled. And this quantum entanglement persists forever in the absence of other interactions. And one, at first glance, surprising fact that we found together with my collaborator Adrian Floyer at Stony Brook, who is now at Brookhaven, is that if you evaluate the corresponding entanglement entropy between a fermion and anti-fermion, then this entanglement entropy can be evaluated exactly using Bogoliubov transformation. And you can also evaluate Gibbs entropy of produced pairs, again, using the same Bogoliubov transformation. And it appears that the Gibbs entropy of produced fermion-antifermion pairs is identically mathematically equal to the entanglement entropy between fermions and antifermions. So we also found that this entanglement entropy can be reconstructed from the moments of the multiplicity distribution of produced fermion-antifermion pairs. And we found that, in fact, a very similar work was first done by my good friend Leonid Levitov and Klish when they discussed shot noise in quantum point contacts. And with Adrian, we also found an efficient way to resum this series, which is only a asymptotic series. And it appears that, you know, if you have access to just a few moments, let's say 3 moments of multiplicity distribution in pair production, which can be measured in experiment, and in condensed matter setup, you know, can be easily measured from shot noise, then you can get a very accurate, you can extract very accurately the entanglement entropy. So now for short electric pulses, it was known that the entropy of produced system looks thermal, and let's say if you have a pulse of duration tau, then the effective temperature of produced system is 1/2 pi tau. So this requires that this tau is much shorter than the adiabatic parameter in pair production. So in spite of this apparent thermal nature, the system remains fully quantum, and you can eliminate this quantumness by looking at a series of pulses, symmetric or asymmetric pulses. And if you have several pulses, then you get quantum interference. And, you know, so this shows that this is not a true thermal system. So this quantum interference clearly illustrates that this is not truly a statistical system. So this is the work that we did very recently with Adrian and Gerald Dunn. Nevertheless, a single short pulse produces a maximally entangled state with a thermal entropy. So really, you have maximal entanglement between fermions and antifermions, and this entanglement entropy is equal to thermal entropy of produced pairs. So this raises a somewhat philosophical question of why does the entanglement entropy of a maximally entangled state have the same form as a classical entropy of an equilibrated system. And maybe what we perceive as a classical equilibrium in statistical physics is actually a maximally entangled quantum state in which some information has been scrambled or is inaccessible to us. So to move along this path of trying to understand the physics of entanglement, we can ask the following question. So suppose I produce a pair of fermion and antifermion, for example, this time not through finger process, but E plus and minus annihilation. And then I have, let's say, confinement. So this is a quark and anti-quark. As they separate, this confining interaction leads to the production of pairs. So the original charges of fermions are screened by this pair production. So the question is, what happens to the entanglement in this situation? Do this produced additionally pairs screen entanglement just as they screen the charge. So this is an interesting question, which actually even has some experimental consequences, because you can think of measuring correlations between produced pions in quark and anti-quark fragmentation. So these measurements were already done in the past. But to perform this study, it really requires some numerical real-time quantum simulation. And this is what we did in this collaboration at Stony Brook and Brookhaven with Adrian Floyer, David Frankler, my student, Kazuki Ikeda, postdoc at Stony Brook, Vladimir Karepin at Stony Brook, Fuji Shi, who was at Stony Brook and is now a professor at Tsinghua in Beijing, and Kwang-Min Yu from Brookhaven. So what we did is we used the massive Schwinger model, which, as you know, describes confinement and, you know, this screening of charge, and describes chiral symmetry breaking. And then we couple this Schwinger model to two external sources describing produced quark and anti-quark. And then as this quark and anti-quark separate along the light cone, which is shown here in this Christmas tree image, they produce fermion, anti-fermion pairs. And we just do first principle numerical study of this problem. Originally, we tried it on IBM quantum hardware. So it appeared that the current quantum computers are somewhat noisy for this task. So what we did was to obtain these results, we used the Perlmutter supercomputer at Berkeley. So this is the seventh most powerful supercomputer in the world. And, you know, when you do this simulation, you really discover the exponential growth of Hilbert space with the size of the lattice. Because, for example, on 12 lattice sites, you can do the computation on your laptop. But for 20 sites, you need one of the most powerful supercomputers in the world. So what is shown here is the screening of external electric field by produced pairs. So here on the middle plot, you see how the scalar fermion condensate is destroyed by the propagating fermions. And finally, this plot shows the real-time dependence of the entanglement entropy. And you can see that indeed this fermion and anti-fermion are entangled. And as you know, the sources separate, this entanglement entropy grows. So the real interesting question now is where is this entanglement entropy in the configuration space? So does it spread, you know, along the light cone, or is it limited to some small rapidity separation between quark and anti-quark? If it is limited to small rapidity separation, then this would mean that entanglement is screened, just like the electric charge. So now here is the numerical results that we find. So this is the correlation as the function of rapidity. And you see that indeed, all of these quantum correlations are concentrated in delta eta, where eta is rapidity, region of about 2 units. So quantum entanglement seems to be screened just like the original charge of is screened. And so if you really want to hunt for this quantum entanglement, you have to limit your searches to small delta eta. So now, finally, let me come to my last topic, which is how could we use entanglement as a probe of phase transitions in chiral matter. So this is the paper which we are now finalizing with Kazuki, Rine, and Fuji. And here again, we use as a model Schwinger model near theta angles near theta angle equal to pi. And the reason we are interested in this particular setup is because the phase diagram of Schwinger model near theta equals to pi possesses an interesting structure. So when mass of the fermion over coupling constant is large, then you get a line of first order phase transition. And the physics of this first order phase transition is very simple. In Schwinger model, finite theta angle breaks parity and is equivalent to background electric field. So when theta is less than pi, the orientation of this electric field is to the left. When theta is larger than pi, then orientation of this electric field is to the right. So you really get some ferroelectric system. And there is a potential barrier that separates these two phases, which is this line of first order phase transition. Then at some critical value of the ratio of fermion mass to coupling, which is about 0.33, this potential barrier disappears, as you can see from the effective potential after bosonization, and you get the critical point where the dynamics becomes approximately conformal. And finally, for very light fermions, for small m over g, when fermions become so light, they just screen this electric field altogether, and you get to a screened phase. So you can see it's, even though, you know, this is a very simple model, QED in 2 dimensions, it actually has quite interesting phase structure. So what we have observed before, also through a digital quantum simulation, together with Kazuki and my former student, and then postdoc at Brookhaven, Yuta Kikuchi, who now works as a research scientist at Honeywell Cambridge Quantum. Near the critical point, if you look at rate of topological fluctuations, which physically just represent the rate of fluctuations of electric field, this topological fluctuations or real-time Chern-Simons fluctuations exhibit a very sharp peak. So this is not surprising because here, you know, switching from one orientation of electric field to another does not cost you much energy. And so that's why you get this sharp peak. But what we have now also observed through a quantum simulation is that if you look at entanglement entropy of this system, then entanglement entropy also exhibits a very well pronounced peak in the vicinity of the critical point. This is also reflected in the entanglement spectrum as well. And the associated physics is quite interesting. When you are away from the critical point, you are in the gapped phase. And so entanglement entropy only depends, on some small spatial region on the order of inverse mass gap. But once you get to the critical point, then the system starts to behave as approximately conformal system. And the entanglement entropy starts to grow as a logarithm of the size of the segment, just like it should in a conformal field theory. And you can also detect this by looking at the entanglement spectrum as well. Okay, so this is pretty much everything I wanted to say today. So I would like also to leave more time for discussions. So let me come to my final slide, which is very simple. I would like to congratulate Maria, and wish her to enjoy time with family and friends, but also to ask her to please let us stay entangled with us. And, I really hope to keep collaborating and discussing and talking with you in the future. So thank you so much.
Dima, for this talk. So, is there any questions in the audience for Dima? Yes, there is one. It's Karl asking.
Hi, Dima. It's Karl.
Hi, Karl.
Hi. Yeah, I have one question about this entanglement spreading in this case where you have confinement.
Right.
In some sense, this is a very surprising result. No, I don't know, naively, if I think about this, why the entanglement wouldn't, would feel this confinement to you? The entanglement, there must be some entanglement swapping, which goes in, to the degrees of freedom which make up the entanglement. Do you have some physical mechanism for how this works?
Yes. So. In fact, the original picture that we had was indeed the entanglement swapping, which is, as you know, is being used in long-distance quantum communications. So somehow we expected naively that the entanglement of the pair would be spread along the entire light cone, because this extra production is also coherent and so on. But then it appears that if you look at correlations, so what is shown here really is the correlation between the scalar quark densities at different rapidities. It appears that these correlations between scalar quark densities is really screened at large rapidities. So, as the charge of original pairs gets screened, then much of the quantum correlation gets screened as well. So, honestly, I have not fully absorbed the meaning of this result yet, but that's what numerics tells you, and whether or not maybe there are some more subtle quantum correlations which still persist along the light cone, and maybe there is a better way to detect them than looking at the scalar quark correlation. So these are open questions.
Okay, thank you.
Any other question for Dima? Okay, if not, we thank Dima for this talk, and it was a pleasure to see here.
Thank you very much. Thank you.
Thank you. So it's time for the next speaker, which is Karl Landsteiner from IFT.
Well, instead of thanking anybody, which Belén has done most, but officially I'm also organizer. So anyway, thanks to Belén, she did most of the work. And of course, congratulations to Maria. Okay. So this is, I'm not giving so much a physics talk, I'm just giving sort of a review how I got to know Maria, our work together, and the history of all of this. Okay, so here is how it all began. And it doesn't mean that we went to kindergarten together. We did not. Yeah. So what this symbolizes is up. Okay. Let me see. I should be able to manage to do this. How do I go? Yeah, okay. So sorry. One has to be careful with this device, yeah. Okay. Yes. So this is what is called caseta. That's here on campus. And this is where the kids, you know, there's the school just across the street. Here's the school. And after school, the kids go here and have some afternoon activities. And then when this is over, the parents come and try to pick them up. But the kids don't want to go home. They want to stay playing there in these meadows. And so one day this happened, you know, and my kids stayed there and played, and there were more kids, and you talk to the parents. And so I talked to one of the parents staying there and say, hi, what are you doing? And he said, well, I'm a physicist. And I said, well, I'm also a physicist. And so I said, so what are you doing in physics? Well, I'm a theoretical physicist. And I said, oh, I'm also a theoretical physicist. And so what are you working on? Well, I'm actually working on topological matter. And I said, oh, me too. And this is very interesting because he was working here, it's Pablo. And so I invited myself to give a seminar at ICMM. It's very dangerous if you meet me somewhere. I invite myself always to give seminars. So, and the reason why I did this is at that time, you know, my hobbies were transport phenomena, anomalies, chirality, Kubo formulas, and gravitomagnetic stuff. So this is something which Maria likes very much, using gravity to derive transport phenomena, etc., etc. So I thought we can probably talk about this together. And so here's a little bit physics. Of course, when it's called, you know, a view from the Dirac cone in your talk, there should be at least one Dirac cone. So here's my Dirac cone. And of course, you have a Dirac fermion. And most famously, if it's massless, you can decompose it into left and right chiral fermions. And then these chiral fermions, they are described by this very, very simple Hamiltonian, which just tells you that, yes, and depending on the sign of gamma 5, this is either plus or minus. And that tells you that the positive energy states have their spins aligned with the momentum for the plus sign, whereas for the minus sign, the spins have to be anti-aligned to the momentum. So this is what is, you have the spin momentum locking. So helicity is determined by the chirality. And here's a happy chiral fermion. In the original presentation, it was rotating, but I had to transform it to PDF. So it's not rotating anymore, but it's still happy. And if you have seen Breaking Bad, you know why right-handed chirality makes you happy, right? So, okay, and then anomalies. So this is the famous triangle diagram, right? So this is the pi zero. There's this famous formula derived 1969 by Adler, Bell, and Kharzeev, and it explains the decay of the pi zero in high energy physics. So that was a riddle until 1969 because the charge pions are very long-lived, whereas the neutral pion is very short-lived, and people didn't know why. And then they found there's this additional contribution to the divergence of the axial current, which is basically the vertex here. And so the pion can decay in these two photons. That's the usual anomaly. Interestingly, in 1969 already, Kimura generalized this result to the decay of a pion to two gravitons. It's very little known that this sort of gravitational anomaly was already derived in 1969. It was published, of course, in a Japanese journal, so it was not noticed by anybody else. That's why it was rediscovered 3 years later And also there was a Nobel Prize winner on that paper that was also forgotten until it was rediscovered in 1967 again. So, but of course, if you ask how much does this contribute to the pi zero decay, I mean, this is suppressed by some 40 orders of magnitude. So this doesn't really contribute anything to this. But it turns out that when you have such chiral fermions and anomalies, there are specific transport phenomena which are direct consequences of these anomalies. And so the most famous one is the chiral magnetic effect, generation of a current in a magnetic field, similar generation of an axial current in a magnetic field. And the same thing works with rotation when this is called chiral vortical effect. And so I've encircled here these two terms which play a role in our works, which is the temperature dependence, which surprisingly is related to the presence of this gravitational contribution to the anomaly. And this is also a specific hobby of mine, which goes under the name of consistent anomaly. Okay. So, but how did we go there? So personally, how did we got involved in this? Well, as a physicist, you know, as a theoretical physicist, if you see some complicated object in nature, you make a simple model. And that's the essence of the ADS-CFT correspondence. So, for example, you have a complicated quark-gluon plasma, and it's just a black hole in de Sitter space from the ADS-CFT correspondence. And you don't care about if it's a plasma or whatever. It also works for superconductors. So the plasma is very, very hot. Superconductors are very, very cold. But you still can make a model where it's just a black hole in de Sitter space, and you find phase transitions and all these modes and so. Very nice. But for anomalies, it's even nicer because it's a topological property. And in this case, you know, the point cow approximation works equally. It's actually exact. So all topological effects you can model and you get exact answers like that. Okay, so this was my state of knowledge about this field at that time. And then I came to ICMM. I'm sorry, so I don't have any photos. Sorry. And I can't draw very well. And even these drawings I have sort of stolen from some, you know. So this was then in, I don't know, 10 years ago, a little bit more than 10 years ago. I gave the talk at ICMM. And then it turns out, you know, I heard about this thing, condensed matter, vial, semi-metals and so on. I said, listen, I heard you have lots of vials. I have lots of anomalies, and sometimes they're even consistent. And Maria was just coming back, and Fito, and is this true? I remember you had long hair. You see? and so Maria said, okay, let's write a paper. Okay, but the story is not complete, right? Because there's one ingredient missing. Not so fast. Somebody is still missing, and that's Maxim. And Maxim I met earlier in a workshop in Trento, which was organized by Dima and some other people. And I told him, listen, there is this thing, you know, this axial magnetic field, and it generates an energy current, and can't you simulate that? And Maxim said, okay, but this is really the last time I do lattice QCD. I want to do nanophysics from now on. Right? Nevertheless, so he contacted his friends from lattice group, and they did the simulation, and then this paper was generated. And then Maxim also came to Madrid, and then we talked to Maria, and then finally we wrote the paper, right? And the paper is, you have this generation of an energy current in an axial magnetic field when you have temperature. And so these vial semimetals, what they do is they have in the Brillioson momentum space, they look locally like vial fermions, but they're separated. These cones, vial cones, are separated in momentum space, and that's inside the material. But if you go outside the material, there are no such fermions. So morally speaking, they're very, very heavy or infinitely heavy. And in order to make two vial fermions, so this is a positive chirality fermion, this is a negative chirality fermion. But in order to make them heavy, you know, you have to bring them together. to a Dirac fermion, and then you can give them a mass. So that means when you have such a material like this, inside you can have these wild fermions, but outside they have to be massive. So in between, this distance between them in momentum space has to go to 0. And so what we realized is that that thing going to 0, that this distance in momentum space going to 0, this is actually this axial magnetic field. It's like a magnetic field, but it acts on with different signs depending on the chirality of the fermions. And so you have this intrinsically built in all of these materials, and then you can argue that there are actually edge currents running around such a material. And I think this is really the first time that the idea that this Fermi arcs, it was known that there are these edge states, but they can be viewed as lowest Landau levels of this axial magnetic field. So that was our first paper. And then we said, okay, now we have this axial magnetic field and it's completely built into the geometry of this model. But it would be nice if we could manipulate and generate this axial magnetic field. And then with Iago and with Alberto, we found that indeed you can do that, but by strain. And this goes back to lots of developments which I've mentioned today already, which originated in graphene, where you strain graphene and you get also this pseudo magnetic fields. And we were able to transport this to this wild semi-metal material and get also, so these are elastic gauge fields, but for the high energy physicists, we can think of it as axial gauge fields, coupling with different signs to left and right-handed fermions. And sort of as a side product, we also found that there's something like a Hall viscosity for the phonons in such materials. Okay. And then there was a workshop in Sweden, and there was Dima there somewhere in Sweden, and it was all about chirality and chiromagnetic effect and so on. But the interesting thing is we had this conversation, right? So notice this little blue strip on the laptop of Dima. And so that was before we went there. I had my laptop and I had some sort of duct tape, papel de celo, so non-transparent, over the webcam. Because, you know, there are these rumors that people can spy on you when you have your webcam. So you want to cover it, right? But Maria didn't believe. She thought I'm totally paranoid, which might be true. I don't know, but but then we went to Sweden, right? And Dima opened his laptop and he had also covered it by this. So and then he told us the story that, if I remember correctly, it was squirrels coming into his house in the roof. And he wanted to install a webcam to see where they come in. And so he discussed this with his wife in Russian, by the way. And so his iPhone was listening, like all the phones are listening to us all the time. And then when he went to Amazon, it automatically, you know, he received lots of ads for webcams. So apparently they also have good translators. And that was back in 2016. Only God knows what is happening now, right? So what's the moral of the story is, you know, always remember, just because you're paranoid doesn't mean that they are not after you. And so this you can attribute either to Kurt Cobain, from if you were young in the 90s. If you were young earlier, you could contribute it to Joseph Heller. It's apparently written in his book, Catch-22. Or probably it's completely apocryph. If you are younger than that, then don't worry. I mean, it's lost anyway. So okay, but in physics, we also discussed physics, not only conspiracy theories. And we managed, again, with Alberto's help, to make now, before we just had magnetic fields, but now we could also do electric fields. And so the idea was, in equilibrium, you don't have this kind of magnetic effect. There is no current generated because the Fermi surfaces are at the same energy. But if you're able to move not the distance between these two wild cones, these points, but their height, their relative height, then you can generate a situation like this. And then the system would have to equilibrate by generating a current, which moves the right-handed fermions to the left-handed fermions. And that's the chiromagnetic current, which is written here. Okay, and so we figured this out, and then we wrote a nice paper and we sent it to PRL, and then nothing happened for a long time. And then this idea caught on, and other groups were building on that and writing their papers, and their papers got published, and they got published in like fancy journals, and we were still having no news, right? You remember? Yeah. And so many months later, Maria finally, said, okay, enough is enough. And she wrote an email, dear editors, please get your act together. I mean, she wrote it much more polite like this, but the meaning was basically this. And then lo and behold, within days also, the paper was published. And I pressed the wrong button again. I'm completely lost. How do I? Ah, here I am. And presumably it's this thing. Right? Yeah, okay. Okay, and then last but not least, a favorite story is torsion. So there's a lot of confusing stuff about torsion. And at the time, so 2019, there were appearing lots of papers on the archive which talked about torsion in relation to transport, phenomena of chiral fermions, and so there were talks that of oops, that was now really bad. Yeah, no, don't worry. Everything's under control. Well, relatively speaking. And so there's an old ongoing discussion about if there is a torsional anomaly. People suggested the chiral torsional effect through the Ni-Yan tensor. In condensed matter physics, it's known that these locations can be described by torsion. And so one day Maria came and she said, we need to study torsion. And so we set up a study group here. And little did I know that I was entering treacherous waters. And but it was good because the pandemic was coming, so I had something to do and study during the pandemic. And the reason, so why it's treacherous? Because of this. So that's sort of an insider joke. So the prophet pronounced torsion is trivial, right? But there are all these papers, and I mean, there's really torsion. You can look up books and reviews that are, there are reviews, hundreds of pages on torsion and torsion in gravity and so. So why it's trivial? And in a sense, it's trivial. And the reason, a formal reason is, if you compare, right, here we go. Why it's trivial, a formal reason is, if you compare it to the anomaly, so there's the anomaly, the field strength in terms of the gauge field, and then the anomaly is FHF, and it's the total derivative of the Chern-Simons form. And of course, that's not gauge invariant. The connection, the gauge field transforms like this, and it has this inhomogeneous term. That's very important. If you compare this thing which has been suggested as a torsional anomaly, that looks like this in terms of the field bind. And again, this Ni-Yan form looks like this, and it's very similar to a Chern-Simons term. But there is one crucial difference, and this is the field bind is just a usual tensor. It has no such inhomogeneous term in its transformation properties. And that makes that this form here is globally well-defined on a non-trivial, topologically non-trivial manifold, whereas the Chern-Simons form is not globally well-defined. And you can see this in the famous monopole bundle, where you have a connection on the north hemisphere, on the south hemisphere, and on the intersection on the equator. These two connections can differ by gauge transformation, and this gauge transformation might have a binding number, and then you have a monopole number. And so this is real topology. But with torsion, this, at least in this form here, that's not possible because the field line is really a tensor. So I think what Mr. W meant when he said this is probably this. Okay, and so yes, this is how we spent Yaga and I spent the, motivated strongly by Maria, we spent the pandemic thinking about this, and then we wrote a paper and talked about the chiral responses due to torsion, and it turns out that there are none. So if you carefully look to it, the thing which was identified or claimed to be a torsional effect can be perfectly understood as a disguise of the chiral vortical effect in its disguise as gravitomagnetic effect. So it's a coupling to the field line, but you don't need to introduce torsion. It's okay with the usual gravitational fields. Okay, so, and much of the scientific part of this story is published in a recent physics report. Sorry for the low resolution. I just pulled this down from the internet together with many people here in the audience, Maria, Alberto, Iago, Maxim. Okay, that's all I want to say. I want to say above all, thanks for the wonderful collaboration and for introducing and teaching me about the beauties of the Schmutzphysik. Okay, thank you.
Thank you, Karl. I was a slimmer in the. I was a slimmer in the.
Yeah, I'm very. Yeah, that's why I didn't make any photos. I think.
Okay, is there?
What shall I say?
Is there any question in the audience for Karl or his capabilities on drawing? No. Very short format. Please go.
But you know that it's important for entanglement to get entangled through kids, right?
Yeah.
So
exactly,
then it's just spreading, like, and we see in the previous talk, you have this kind of spreading of entanglement. And
exactly.
Let's be logarithmic.
Okay. Any other comment or question? Okay, no, we are ready for the coffee. So we thank Karl for this talk. And oh no coffee yet. Sorry.
Yeah, sorry for the misprint, but there is
Well, is a break-in? No coffee.
because we need to be on time.
Okay. Sorry. So then let's move on.
Okay, so let's move on. Let's see if Mauricio is here.
Not see my presentation.
Hello, Mauricio.
Hi, how are you?
Good.
Okay,
Very good.
Now I see.
Okay, so it's a pleasure to me to introduce Mauricio. Mauricio was here for a while. He will tell us about it. And he's now in La Plata, Argentina. So please, Mauricio.
Okay. Thank you for inviting me to participate in this special workshop to honor Maria. I want to thank especially to you, Belén, and to Alberto for inviting me to give this presentation. I will not talk about any technical stuff, but about my personal experience being a postdoc in Maria's group. To start from the beginning, I did my PhD in string theory, and at that time I was decided to shift to a more applied field. So I started to explore the possibility of use Dirac fermions coupled to metric perturbations to describe the interaction between fermions and phonons. But of course, at that time, I didn't know nothing about the existence of graphene. So I explained this to some of my high energy colleagues, and as far as they are all sensible people, the answer was that, of course, that it was nonsense. But one guy told me that he had just attended to a talk in which a speaker presented a real material, 1 atom thick, in which the physics were explained by Dirac fermion in Karl space, and that he could put me in contact with the speaker. Of course, the material was graphene, and of course the speaker was Maria. I was very nervous about to write her an email. So it took me a lot of time to write that email, thinking what to say and how to say. So finally, I wrote her my email, and just after a couple of hours, she answered me and asking me to talk by Skype. So we talk on Skype, and I think that's one of the beautiful things of Maria. She's so enthusiastic, and she never postponed anything. So we talk by Skype, and she invited me to visit her. And a couple of months later, I went there in Madrid to give my talk at, at the ICMM. I prepared my talk, and so I named it something like a graphene from first principle calculation. It was funny because coming from high energy physics, I didn't know that first principle calculation was another name for ab initio computational technique. So I think that I disappointed half of the audience that were expecting some numerical news, and perhaps the other half because I was saying things that they already knew. But anyway, I finished my talk, and when I was done, I asked to Maria, what do you think? How was my talk? And she said, oh, pretty nice. You said some nonsense, but nobody noticed. So Maria hired me anyway. And 6 months later, I went back to Madrid as a postdoc. So before going to Madrid, I took some time to read the bibliography and study some basic of condensed matter. So I took it seriously. So I bought the Ashcroft and Mermin book. So starting to read. And when I went back to Madrid, I mentioned that to Maria. And it was something like, hey, Maria, I bought the Ashcroft and Mermin book and starting to read. And Maria told me, oye, Mauricio, ¿tú estás tonto? Something like, are you not? I'm hiring you to do Fermions in Karl space, not tight binding computation. But our first paper was, of course, a tight binding computation. It was a very nice idea. Fernando and Maria, and they invited me pretty generously to participate in it. At that time, Fernando was at Indiana, I think. So we wrote emails every day, and then we spent a lot of time with Maria discussing at the blackboard. Actually, I think it was a green board. I don't remember, but I think. It was a very fun time, and also very productive. I have to say that those discussions, together with the discussion that I had with Alberto, that was my office mate, served to me also as a crash course on Madrileño, and I still today, these words come to my mind on many occasions. Of course, I try to not use it here because it sounds very weird. Of course, some of those words I cannot repeat in public. But okay, we collaborate on other papers, and also always Maria was very sharp and very clever. But she is also a very good storyteller. So her papers are always very well narrated and with a very clear message. So I mean, in such a way that you always enjoy to read a paper of her. This is a lesson that they took to me, and I try to apply to myself. I had a wonderful time at ICMM during my postdoc, and I attribute much of that to the influence of Maria. She created an extraordinary atmosphere of collaboration with a lot of seminar groups and discussions everywhere. We also used to have very amazing lunch, sitting at round tables with a lot of people, 6, 5 students, 4, 5 postdoc, and Maria, who used to be, many times who used to be the only senior. And we had a long conversation, always talking of politics and always in a fun way, funny way. So I am pretty grateful for the opportunity to have been part of her research group and to have learned from her. These are some pictures that I found in my computer of the Maria students. I have different pictures because in some of them there is Fito, and in the other one it's Fernando. Okay, and that time my daughter Emma was born, and being parents for the first time in a foreign country and far away from our family was not easy. And there was Maria again, helping, being supportive, becoming for us in a way like a family. So I spent one of the most extraordinary time of my life there in Madrid. So I simply want to express my gratitude to you, Maria. Thank you very much.
Thank you very much, Mauricio.
Thank you. Thank you, everyone, for staying here after the coffee break. So I'm going to start not mentioning the Dirac cone, but the Dirac string. So because as you can read here, is a kind of highly unlikely journey, how to put Dirac strings in a contest matter setting. So this is the guy I eat a couple of years ago. So, okay. So let me start with a couple of lessons I learned from Maria. And I guess this is something that I'm going to share with Adolfo, with Fernando, about how to be a scientist as a whole. Not as a whole, as a whole. Okay, so the first lesson was, as you can read here, is that cosmic string. So, well, really? So, taking the advantage that Paco introduced the Facultad de Ciencias Físicas de la Complutense, I can say that things changed from that time to the time I studied here. It was by the end of the 20th century. So now things were more quiet. And well, actually, what I want to say is that I have to say that probably the quality of teaching was better than at that time. In any case, not in the case if you wanted to be a theorist, because at that time all the subjects related to theory was exhausted by high energy people. So when I was looking for a PhD, I have a friend already starting here, and he told me about what happened if I started a PhD on contest matter. And I said, no way. Why? Because the things I knew about contest matter at that time was that, okay, Ising models. So I don't want to thermalize Ising models by no means. And also, which is worse, I don't want to solve the Bowman equation at all. Okay, what I really wanted to do is just to do beautiful things like Feynman diagrams and, well, cosmological stuff like analyzing the universe and so. Then Maria, well, I had a meeting with Maria, and that happens that day, Maria was giving a talk here in the ICMM. And he was giving a talk about this particular paper he published with Tobias Stauber and Paco Guinea about disordered interactions. And she said, wait and see. And he started to fill the screen with the Dirac equation. That is something I was here about during my undergraduate studies. And also, he drew some kind of Feynman diagrams. not exactly the same that the one in the previous slide, but okay, they were Feynman diagrams, and most importantly, there was a Dirac equation in condensed matter. And also he spoke about how the Fermi velocity renormalization we heard about in the previous talks was already affected by this order. So I say, okay, yes, I like it. So I had to learn as Mauricio condensed matter or solid state at some point. In any case, he gave me a couple of references. One of those was these two papers about also co-authored by Paco. He mentioned already in this morning about the Dirac equation on the Fuller ring. And he just, when she explained this to me, she just ticked some kind of ticks. So Dirac equation, okay. Karl space, okay. Gauge fields, okay. I like it all. Okay, so I mean, so we start to discuss about this and how to work out on this stuff. And one of the ideas that came to our mind is this: how to put pentagons not in Fuller rings but in the flat space. Well, to make the story short, so we found some references concerning how the cosmic strings appear in cosmic background. Okay, why not? Let's put them on graphene. And this is what we did. Just wrote some kind of funny metric background. We solved the green function for fermions in a Karl space with this particular metric, and this is what we got. So we got some funny stuff. One of those, I think, didn't realize that it was so important. That so kind of quasi-localized state in the cosmic string. At that time, we had nothing about I didn't know anything about cosmic things, so we didn't realize how it could be interesting at all. But the funny part, it was beautiful. And this was one of the lessons I learned from Maria, that physics can be beautiful, not only useful. Well, I think what is more important is beautiful. So, okay, we generalize this from having several of them, several cosmic strings. We publish some results. This is funny because at that time there was this problem in graphene, which is what's so-called the missing pi. So essentially, experimentally, people observed that the samples of graphene were more conductive than they were expected from very theoretical grounds, and we end up with some very funny theoretical non-linear sigma model stuff to calculate the conductivity, and actually we got a bigger, larger than p conductivity, so we didn't solve anything at all. But at least what we found is that the conductivity in graphene was not truly universal as it was thought at that time. Okay, so as you know, it has a twist sense of humor, and something I told you at the beginning, that the Boltzmann equation was the worst thing in the world. I found myself working actively in this particular topic. Also, recently with my student in terms of hydro transport in basic metals. Anyway, so just go quickly to the second lesson I learned from Maria. And this is something I really want to apply as an advisor. I failed miserably, which is how to not sign a paper. Okay, so this was it's another story about graphene. So at that time, graphene was proposed to graphene as using this claim tunneling stuff, and how to use this the p-n junction in graphene to get a Valley filter. You know that in graphene there's this Valley degree of freedom, which is similar to spin, or it's often called pseudo spin. Okay, with Juan Luis, which was the guy who introduced me here, who introduced me Maria. He was working on optics. We made this paper. Well, the funny thing is that Maria put a lot of input on that particular paper. Oh, sorry. But the funny thing is that Maria did not sign that paper. Okay, why? Because, okay, she didn't need it, and she was a mentor there. She was helping us. She was helping me a lot also with the English. My English was, well, if my English now is broken, imagine that time. So, and she helped me a lot with this paper, and she refused to sign that paper, essentially because he was her duty just to help me with the research. And one paper or another was not important. What was important is how to tell me just to go to the pool and instead of shrink, just to swim. And well, later on, it happens that this paper was published in 2008, and in 2021, they started to be observed. It's an experiment, and also this kind of stuff has been already proposed to make these funny quantum photonic circuits and this kind of stuff. So this is the second lesson I wanted to also, it has been already also observed in these optical analogs of graphene. And for other reasons, I like to thank Maria, because she also helped me to stay in academia for the reason. So, well, she tried to do this is the picture from my PhD dissertation, and she was actually trying to keep myself in academia. So, thank you, Maria, for that. And well, you know, I can tell you how much I debt you for me as a scientist. So, thank you very much. Oh, yes.
Esto vale. Se llaman todas iguales. Esta. Vale. A ver. Este es el puntero.
Y está para adelante.
Okay. Okay, shall I start? So I'm the second. I'm Fernando. I think there's going to be a bit of overlap. I'm actually surprised that my beginning is the same as Alberto's beginning. So if you've talked to Geli in the blackboard many times, when you start writing an equation, the first thing she'll say is, wait, I don't want to see this. Where do we come from? Where are we going? So where do we come from? So this is me in 2006. This is where we come from. And as Alberto, I was a clueless graduate with a little background or inclination to condensed matter physics. I had taken no courses in condensed matter, almost at all. I spent most of my last year doing field theory with Tony, actually, who just left, and gravitation. I spent like 6 months contracting Christoffel symbols, and I thought, where should I do my PhD? And it turns out that there's some further neighbor connection through. So Maria's sister is a friend of my mother. So somehow Maria found out that I was going to do a PhD, and she called me and said, wait, if you're going to do a PhD in theoretical physics, I will tell you who to work with and who to avoid in her very characteristic style. She said, this person is recommendable, this person is not recommendable. And so we started talking, and in the end, I came to her office, and I also learned about what they were doing here. And in the end, from this conversation, she ended up getting a new PhD student, and I didn't do a PhD in any of this. And that's how I joined. And I started doing condensed matter through the Dirac equation and cross spaces as well. And so the first problem I tackled was actually from a discussion from Alberto and Maria when they were explaining this cosmic string thing to me, and they were saying, we're solving the Dirac equation in a singular background. And I remember saying, why did you try singular background the first time? What's up with the smooth one? Why don't you try something smooth? And immediately Maria said, that's your project. Go. Please come up with some smooth background and just solve the Dirac equation with it. And so since I had done some Christoffels for general metrics, I tried the metric of this bump, which we used to call el bollo. The bollo is like a bump, right? This paper has been known as el bollo ever since. And that's what I did. I look at, I made the metric for this, and then I solved the Dirac equation, and we published this paper. I was very lucky to publish a paper almost right away since I joined. And I was very happy about this. Something very remarkable about this paper, I opened it after a few years, is that there are no axes at all. So there's no Armstrongs, no energies, no electron volts, there's nothing. There's 5 figures and no units at all. It's amazing. but it went through referees right away. It was it was great. And so I was very happy saying, right, I mean, curve spaces are useful in condensed matter. So let's try to tell this to people. And we got into trouble immediately because no one believed this. And the reason is that people expected a tight binding calculation, like Mauricio was saying. And so this is a problem that actually chased me for the rest of my PhD and even beyond that. So this is what graphene used to look in the early days. It had all of these bumps, and this was the motivation to study curved surfaces, or Dirac equation in curved surfaces. This is what people from a condensed matter background would have tried first, a tight binding model where you move the atoms and put the strain in this way. And everyone was telling me that these two things should be the same, or at least if my model was to be correct, it should reproduce what the tight binding gave. And this left me puzzled for a very long while. And I actually defended my PhD without knowing the answer, whether these two things are equivalent or not. And this was work that came after the PhD during the postdoc years. As Mauricio said, I had already left for Indiana. But this was the origin of a very fruitful collaboration with Maria and also with Juan Mañez and Mauricio, where we did all of these works explaining how to model strain and how does it match to curve space and so on. And ever since, we've been receiving emails every 6 months or 1 year saying, this was wrong, you need to do it again because my calculation says something else. And we've been iterating, and well, it's been fun. And one thing that happened very recently is that actually there was a postdoc from Oxford that tried a numerical calculation to see how these two things match exactly. And it turns out that there's a problem, which is the Landau levels in a curved background, where you can do the numerical calculation in tight binding and write the Dirac equation with curved metric and magnetic field. And there is an analytic expression for the Landau levels, which is square root of 2b plus something with curvature. And you can match it exactly with the tight binding model without very parameters. So this is the one example I know where it really worked exactly. So I was very happy to see this conclude so many years later. But yeah, this was a long ride. So this was actually not from the PhD, but coming from the Boyo paper. The next thing we did was defects, as Alberto was mentioning, from the cosmic strings and the pentagons. We were working with, right, if you push it for too long, then it goes out. We were looking at these locations, and I tried the numerical tight binding calculation, and I found this zero mode in the octagon mode, and we have no clue where this came from. And this stayed for a while. It also led us to other work like what Pilar was presenting, the topological defects and how they affect magnetism and so on. And also to the torsion paper that I also work with Maria, where I already heard from Mr. W that torsion is trivial when we started, and we still managed to write a paper about this, where we essentially said more or less the same. Torsion is not as critical as one would think to describe these locations. And again, this was something that led me very past for a while, why there is a zero mode here. And this is another thing that I also looked at in my postdoc once I learned the topology of band structures. And there's a deep reason why this zero mode is there when you have particle hole symmetry. So there's a topological reason for this. So that was also part of the PhD. Then there was the trip to Santa Barbara, which I really enjoyed very much. So Maria took me to KITP in 2009. We were there for a month. We actually went to San Francisco first and did some tourism together. I think this is from Santa Barbara, not from San Francisco. But that was a lot of fun. There was also the time where I learned a hard lesson in research, which is you need to learn when to abandon a project and go do something else. And the reason is I had been working on a problem with disorder field theory for Dirac fermions from a study that I did in Germany, and it was going nowhere. And one day she called me to the office and said, this is going nowhere. You need to just quit and do something else because it's burning you forever. And my answer was no. I said, I'm not quitting. I will take this to completion and finish this paper. And about like 2 or 3 weeks later, I thought, yeah, no, let's abandon this. And in the meantime, we met Eugene in Santa Barbara, who was working on these things. And it was, the good, if somewhat traumatic experience of learning how to pivot and use what you have learned to work on something else, do a different project, and publish a paper with this. And this is what I did. This is another paper on disorder, which we did with Eugene, which, I mean, it was a bit different, but it was at least a paper. And well, that's another lesson to be learned, when to stop doing something and do something else. The other big part of the PhD was the renormalization and the Coulomb interactions in graphene. And for that, we also have the help of Adolfo, who joined more or less right at that time. As this has been mentioned before, we studied Maria's paper on renormalization, which is this one here, which is known as the Bible, and we called it the Bible because we kept going back and reading this paper many, many times and computing these 3 diagrams over and over and over in different contexts and calculations, in particular for the optical conductivity. And one thing I ended up taking out of this as well was this seemed confusing until you try to compare with experiments. So this was when by the end of my PhD, I was very focused on trying to match these 2 experiments in some way, and how to use renormalization conditions to measure the running of the Fermi velocity and what this implies for the different experiments. And I guess Adolfo will also talk a little bit about interactions and diagrams, so I'll leave it here. And that was more or less my PhD. This is my defense in the very same room I'm standing now, about, what is this, 13 years later already, where I ended up getting a PhD in condensed matter and, doing several postdocs in different places, and ended up in San Sebastian, where I was now, where I was very happy. So it was it was an intense experience, which ended well. And right after I left, or when I was about to leave, there was a bonus to my PhD, which was this paper we did in collaboration with Andres Cano, who was a friend of mine from Autónoma. He was a student, or he had been a student of Arkady Levanjuk at that time, and I knew him because he was teaching numerical methods. And he visited Madrid right before I was going to leave, and he started asking questions about graphene and interference in STM, and so interference in STM and so on. And I said, okay, yeah, let's work on this. Let's try to figure out if there's something interesting. I left and I started writing some notes. And one day, by the beginning of March, I got an email from Maria that she had submitted this to Nature Physics without me knowing. And I said, I remember this more extreme than it really was. But at that time, I thought, what did you submit? There was nothing. There was no paper here, no calculation. And it was submitted, and I was looking through my records, and more or less everything was there. But the paper we submitted didn't have this plot. So this plot is the numerical calculation I did after the referee report. And it was published in Nature Physics very fast. And there's another lesson to be learned here, which is maybe sometimes I try things to, I try to push things too far and to make them perfect, and things don't need to be perfect. And there is a point where you need to stop and submit and just let it go. And when you have 80%, it's time to start thinking of submitting and not go in loops over and over and over and never do anything with it. And, this was the extreme case where it was submitted very, very fast. And it ended up working all right. And so, without taking much more time, I wanted one last slide on other styles on things, on style and mentioning that I like from Maria. I like how when people ask questions, even in conferences, she's very plain to say, when she doesn't know, I don't know, you tell me. And sometimes it's good to know that you don't need to know everything, and it's okay to answer, I don't know. And this is something I try to do as well. Another one is when I tried to, this is from the La Familia projects, when I asked if I could join a project, and she said, of course, land is for people to work on it. This is this slightly communist revolutionary motto applied to physics, which I agree with. So don't let politics get involved too much. If you're doing something that is worth doing, then just do it first, and then we'll see how everything comes together. No, but if you're really working on something, just keep doing it. Should be worth. And from the RG and interactions story, I also learned that you have the time to study in depth when you're a PhD student. Not all PhD students have this luxury, but I think we did. And it's something that I enjoyed a lot. And, you know, just become an expert in something because you have plenty of time to study, and this won't be like this after that. And the one last thing is that Maria was an advisor through the PhD and also after the PhD. So she was a great advisor, but also after the PhD, she stayed in touch and helped me through my career. And whenever I needed to ask something about, you know, how to navigate the career, this is, you know, something that I could ask, and she was there to answer. And I think this is great. This is something that I will try to do with my students as well. So this, you know, you do a PhD and you get a mentor for life. And I think that's something to think. And that's all. Thank you, Maria, and thank you everyone for listening.
Yeah, okay, so I'm the third observer from the Dirac cone. So I'm gonna try to, yeah, I came after Fernando and Alberto, and the way I came, so it was already mentioned that I looked, I looked a little bit different. I had long hair just as Fernando, so I think this is a common thread. So I signaled myself just in case you cannot recognize me. And this is my kind of closer group of friends from undergrad. And so to the left is Clara, who's Maria's older daughter. And we did undergrad together. And so without knowing, I was doing my undergrad and studying for my exams in my future PhD's advisor home. So, so we went there, actually our hub to study for exams was actually Maria's house without me knowing. And so she already, I don't know how much she knew about us, but I think a little bit, but more than we probably knew. And so when we were ready to graduate, we all came to the, maybe Clara. Maybe Clara is upset that I put her picture. But anyway, we're still good friends. And in fact, I was not the only one in this promotion. So there's Iago here, who was around. And that's Clara down there. So we clearly knew how to choose our PhD advisor. And indeed, when I came, you know, I was told that there was the Bible, and as the Bible does, you have to do Bible studies. And that's this is the Bible, and this is Bible studies. And this is around March 2009, so I was probably doing my master's thesis back then. And already then, you know, this is kind of how as well for me worked. You know, I wanted to do high energy physics, and then you know, we visited Maria, and Maria was like, "Oh, you know, but high energy physics is dead. You just have to." Sorry for. You just have to. You know, here's. You know, you just want to do Dirac. You just want to do beautiful physics, and we do beautiful physics. Look at all these Feynman diagrams. I was like, "Oh yeah." So I was. So she really knew what to say, and obviously she had perfected her discourse. For me, it was just like streamlined, you know. So yeah, so I was very happy to, you know, I was very lucky to have her as my PhD advisor. And I don't know, maybe this story is apocryphal, but this is how I remember it. I remember hearing either from Maria or maybe someone that Maria worked with, I don't know, but this is how I tell my students so that they're afraid of me a little bit, that you need a two-loop calculation to graduate. Of course, this is not entirely true. We actually did a two-loop calculation thanks to this Bible studies, and that kind of ended up in this paper that Fernando mentioned, which actually, by the way, it'll come back later in another paper, because we did a lot of work in trying to understand the optical conductivity of graphene and interaction corrections, and we went through sort of dead ends as well, as you do normally in research, and this came later as a surprise, as a gift. So that's the first lesson I learned in my PhD. Also, I kind of started a tradition, and this is something that I also appreciate a lot from my PhD, thanks to Maria and also Belén. They kind of had a very clear idea of what projects could work, and so you could, you know, if a PhD student starts, you want the first project to work, and that's kind of what happened to Fernando as well. And in France, which is where I am now, PhDs are shorter, they're 3 years. So you really need project that you know is going to work. So this was my first project. It was actually my master thesis, which we happened to publish. We were trying to explain some optical conductivity in graphene, trying to understand whether kind of more exotic self-energies could explain recent experiments. It actually went through, as you see there, it was an editor suggestion. We had like essentially 3 lines for each referee. It was the easiest referee report I've ever seen in my life. And I was like, well, publishing is easy. Come on. This is so well, and they were like, no. This is not how it goes. And indeed, I can assure you, never again. But it was a super smooth experience. I think one of the comments of the referee was, can you change the units of this equation? And like, okay, fair. Okay. And so, yeah, indeed, together with Fernando, and my first PhD student, I also gave him an optical conductivity project, which I knew was going to work, and it did. It was a really nice experience, and I'm really happy that happened to me as well. And in fact, in Santa Barbara, which has been mentioned again and again, Miguel Ángel got to meet the family and extended family. So that was a happy thing. And in fact, I think we already mentioned that Santa Barbara, I think, has played quite an important role for us. In particular, for me, has been really an inspiration to go always to Santa Barbara. And this was my first time. Maria took me with her. There's Hector and Emanuele, who we shared a flat with, and we had a lot of fun. And I think Maria took the picture on the bottom with a lot of equations, and there's a lot of Dirac equations there. And in fact, this work there, it was actually really a nice time to go because Burkholm and Valens had just published a paper about vial semi-metals. So this 3D version of gapless fermions in predicting basically that there were some materials that could realize it. And so I ended up writing this paper in my PhD, which you don't see Maria here as happened with Alberto, but in fact, in a very similar way, Maria, and as it's rightfully acknowledged here, was very encouraging and always, and this is something that I want to highlight, always, I think, with all her PhD students, has been very enthusiastic about their own ideas. And I think that's something that I really appreciated. And I think, she encouraged me to work not only with her, but also with Alberto independently of her, also with Fernando. We had some papers. So that was really nice. And I think this is something that I also want to kind of continue doing with my PhD students if they come with their own idea and they're motivated. And I'm very happy to encourage them. And I think this all comes from her. So yeah, and what I wanted to say is that if you're stuck on a problem and you kind of understand something, that's all right, because sometimes this problem comes back to you. In fact, thanks to a lot of discussions with Fernando and Maria, we worked on these theories that were kind of ill-defined in perturbation theory, looked ill-defined in perturbation theory, but in fact, they were finite. So they had superficial divergences, but in the end, observables were not divergent. And this was an example of it. And we thought it was the case of graphene. It turns out it wasn't. But then it was actually the case of vial semi-metals because they had this vector that you could interpret as this vial node separation that you can interpret as an axial field. So as I said, Santa Barbara has, thanks to the first time I think I came, I think in Santa Barbara, they still have the picture of me with the long hair. And I've been coming, very frequently. In fact, last time it was just I came on Monday from there. So I think it's really always inspiring, and it all comes from that first time I visited. And in all cases, it has been around the Dirac cone. So I think doing the PhD with Maria was certainly key for me to return. And here's a note about the family papers, which have been mentioned. I'm using like a tradition of this institute, which is to glue someone without legs in the back. But yeah, indeed, this was kind of, we were all very serious, except some of but I don't know why I'm serious and Eduardo is serious, but this was more the type of atmosphere that was there. Actually, I recently pulled out my old emails and it was like Maria sent this picture that she took of me saying, just to remind ourselves that physics is fun sometimes. So it was indeed fun in that collaboration, and we actually had a great time and published two really, I think, really nice papers that are relatively, I think they have stood the pass of time. And in fact, we found a lot of interesting phases near Van Hoff singularities and with interactions, Kekule, and so on, that are not kind of being revived in Twisted Bilayer as well. So it's kind of nice to see that this physics is still going on and still relevant. So yeah, indeed, it ended up well. I got my PhD, so that was always good. And I really like this picture of the larger family. Now, actually, in the back, you can see, maybe I can hide it. Yeah, here there's Danny, who is actually now a PhD student. He was a master student with Alberto, and now he's a PhD student with me and Fernando. And we are very happy with him. Also, Maria also kind of nicely introduced me to Oscar, who I really appreciated coming to Grenoble and working with me, and we had a very fruitful collaboration. And in just as a note, this looking at nice problems and understanding them from the point of view of the Dirac equation is always with me, and this is kind of where I always go back to. And in fact, this is a paper we posted very recently on arXiv, and you see that essentially it all revolves in understanding the Dirac equation with space-dependent mass. So that's kind of all coming from what I learned in my PhD, and I think this is a really nice anchor that I always go back to. And so with that, I think I'm gonna end up with this really nice picture that I think summarizes how happy we all are to have known you and been mentored by you. And so I thank you and congratulations, and thank all of you.
It's my great honor and great pleasure to be able to say congratulations to Maria Angelis. We met about 20 years ago at Aspen Center of Physics, and we have met many times since, but somehow not in the last 6 or 7 years since I retired. I'm actually now I'm retired, but at University of California, Berkeley. What was interesting in our relationship was that we always disagreed on what really good physics means. We would always take extreme positions on our opinions so that to get a rise out of each other. Like I would say, string theory and etc., and anything that is happening in particle physics on that kind is completely useless because there are no experiments. And Maria would say, you people still believe in doing superconductivity theory. It is the simplest kind of gauge theory. It's not so interesting. So we would always have polemical discussions like that. But I really got to like her wit and her intelligence and the completely no-nonsense attitude that she had about everything in science, art and culture, and politics, and also in relation to people. I once was in Madrid, where she took me around to Prado, and I got to really, she taught me how to appreciate Goya. On another occasion in Madrid, she taught me the difference between what a good flamenco singer is and what only a moderate flamenco singer and dancer is. One should never let any opportunity not to speak a little bit of physics. So let me see if I can go to my next slide. Maybe that's proving a little hard. Let's see. Oh, now I can do it. Oh, I first wanted to show a picture from about 10 years ago of Maria and Ángel and my wife and I at Escorial when we visited Maria and Ángel in their home near Escorial. And we pretty much, I think, still look about the same. And I look forward again to see Maria. So now to talk a little bit about physics, I was very impressed about 15 or 20 years ago by work that Maria and colleagues had done on the quantum critical aspects of the dielectric properties, non-local properties in the Dirac cone graphene due to photons, or what I would like to say in condensed matter physics, retarded Coulomb interactions. And I actually decided to start taking interest in graphene. And a few years later, I decided to understand the Haldane model for quantum anomalous Hall effect without applying a magnetic field due to spontaneous time reversal breaking. And that thing came in the form of asking how would Duncan Haldane's phase come about. You see it has these, within a unit cell of graphene, it has a anti-clockwise current loop between the red atoms on the sublattice B and the same direction of current between in the sublattice A. And Duncan, of course, proposed it not with any specific realization in mind, but to sort of prove a general principle. Of course, that general principle has become very important due to work of Kane and Melee. But when I looked at this thing, I said, hey, what would happen if, as is more realistic, nearest neighbor interactions are the important interactions? And if nearest neighbor interactions are the most important interactions in the problem, together with on-site, then you tend to get a whole hexagon with upflux and a whole hexagon with downflux. But you see these centers of these hexagons are lying on a triangular lattice, and flux up and down is like a icing representation, and therefore on a triangular lattice that cannot order, except that it orders in this, what has happened here? Excuse me a moment. Okay, well, let me just finish my brief remarks. What I wanted to say was that a certain pattern comes up, which is quite different. And that issue came up again recently when people were making these twisted layers of bilayer graphene. And in calculations done by Ashwin Vishwanath at Harvard and Zaletel at Berkeley and Berg in Jerusalem, you find that basically, even though you're dealing with a large length scale in this twisted bilayer graphene, the basic pattern that happens is currents on a carbon-carbon length scale, which is basically of the form that I just showed you a moment ago. And what's very interesting about it is that if you look at the quantum critical properties of that, what would be the model which will describe the quantum critical fluctuations, it turns out to be the quantum XY model with the phase fluctuations coupled to fermion currents. And it just so happens that that's a model that a few years ago, my colleagues and I solved. And there is some reason to believe that the linear in temperature resistivity and linear in magnetic field resistivity that various people have discovered in graphene close to superconductivity may be related to such things. I wish I could have shown that to you, but that's not the point of this, my presentation. It was again that looking at the work of the Madrid group on graphene got me interested in these issues, and I tried to further the kinds of things that I learned from them. So at the end, I just want to say to Maria, congratulations again. And I retired 5 years ago, and I have never been happier doing physics more in retirement than these years. That retirement is wonderful for doing more physics, and I hope Maria will do that, and I look forward to seeing you people in Spain or somewhere else in the near future. Thank you very much for letting me come and speak in relation to Maria's official retirement. Thank you very much.
Thank you. Thanks a lot, Chandra, for your words. Are there any questions for Chandra? No? Would you like to say something? Maria gets the mic now.
Chandra, you don't look any older. I thank you very much for connecting and for being here. It has been a really very touching journey. And okay, it was fun. It is fun, and it will be fun again. So thank you very much.
Good to see you, Maria. Bye-bye.
Okay, thanks a lot. Thanks, everyone. I think this concludes today's session, and there will be another one tomorrow. So thank you. Thanks a lot. And bye, Chandra. Thanks.
Bye-bye.